Part. We have, it's my great pleasure to welcome Ondra Bojar and in the afternoon Ondra Dušek from Charles University in Prague, having a full day on NLP with transformer models. So this Ondra Bojar will be rather about the basics and machine translation, and Ondra Dušek in the afternoon will be more like dialogue systems and natural language generation. So Ondra Bojar, just notice that we put A after all the names in Czech. Like I'm normally Jan, but I'm Honza, so this is Ondřej, and all the Ondřejs in Czech, because this is difficult to pronounce even for us, are called Ondra. So he's associate professor at the Institute of Formal and Applied Linguistics in Charles University in Prague. He's leading the research in machine translation in the whole of Czech Republic. He actually is behind some important shared tasks in the international evaluations like this WMT. I'm pretty sure he will mention it, and he's just behind like everything important that happened in machine translation in the last 20 years. And just to show you another beautiful place, Ondra just came from Kroměříž. I have no idea what he was doing there, but that was the information. And Kroměříž is a UNESCO heritage site that is also some 60-70 kilometers from Brno. It's not so known, not so crowded, and definitely worth visiting.
Absolutely. I spent my evening in that building and also in the main entrance, which is there, listening to some Cymbalovka music.
Oh, okay.
So sorry for missing out on Brno, but there was no chance
this is better.
I would miss this.
Okay. So Ondrej, yes, you want HDMI? Andrew can do a break, maybe after 1.5 hours, or whichever you prefer.
Sorry. Tak to si udělám. So, good morning. As said, yesterday I spent the evening, singing and dancing, and then I was finishing the slides. So it can happen that I'm not so coherent. So whenever something is not clear, for my pronunciation reasons, or simply for like bad sentence structure or whatever, raise your hand, ask. I'm not sure if I have too many slides or too few slides. That's always risky with these long lectures. And we should spend the time together until 12 approximately. As soon as you start falling asleep or I start falling asleep, we'll make a break. Otherwise, I'm not exactly sure. I double-checked the content of the previous days, and I think that some of the things could have been said, which I will then skip, like the transformer itself. Has anybody covered transformer? That's great. So I have the slides for that, and I can skip that. But I don't think that people are speaking much about text and speech translation. Is that okay? So that's good. So actually, text translation is the area from which transformer comes, and that's why I feel kind of authorized or knowledgeable enough to speak even about language models, large language models, and that's would be the tell part of my speech. And then in the afternoon, the other Ondřej Dušek will come, and he is more interested or working more in dialogue systems and generation from formally specified content. Machine translation is like sequence to sequence, so you're generating from something which is not symbolically written, but it's written by humans in a native language. So the outline for the all 3 hours, or 2.5, I will see how long the break will be, is this. I'll start about the history of machine translation. I'll skip the very interesting parts and I'll skip my favorite part, which is syntax-based translation, because it is today no longer relevant, really. I'll describe at least the very basic phrase-based MT. have you ever heard phrase-based MT before? So who knows Moses? Okay, just a handful of you, and there is plenty of people who have not heard that. That's good. Yeah, you have heard about transformer. I'll mention WMT, and I describe it as the vicious loop of WMT, and I think that this is this strategy of WMT, the evaluations, annual evaluations of models, is something which the large language model community is desperately missing. So it's very fragmented, there are very diverse tasks, and it's difficult to navigate the research of large language models. It is simply too broad. Whereas in machine translation, the goal was pretty simple. You translate from source language to target language, and we developed the methodology how to like do science, how to progress in research in this area. So that's the vicious loop. And then another important part that I would like to describe in quite some detail are caveats on interpreting the results. Because neural networks are very black box devices, they are subject, or you are subject to many misconceptions, and I have some examples from machine translation area. Then I'll also talk about speech translation, because already in 2018 I was kind of anxious that machine translation may be scientifically too easy or developed too far. It's difficult to show it has been difficult to show progress already from 2018 for some language pairs. So that's why I have added speech translation, and you have had quite some talks on speech recognition, right? So I have only one slide about speech recognition on its own, and then I have more slides about combining that with machine translation. And then I'll move to multilingual machine translation. Machine translation already is multilingual, isn't it, right? It has two languages, the source and target. So by multilingual machine translation, I mean machine translation which involves more than the two languages, than the source and target. And that is actually one path through which we can get to what we now have in large language models. And the other part is the one that will follow immediately after that. Technically, like large language models are the decoder part of the transform model. And there, again, I have some caveats on evaluation. I'm closing with just two slides. Very high-level ideas on understanding. People today, again with LLMs, use the terms like understanding, and they even say semantic understanding, because the word understanding is not specific enough to talk about the true meaning of the meaning or whatever. So you see already by the terminology, by resorting to semantic understanding, that even the researchers have a very hard time in specifying what they mean by seeing a model understanding something. So I'm like finishing with two paths through which understanding could be defined. At the very beginning, I was hoping that by doing machine translation, I will have to model understanding explicitly. I was assuming that if you want to translate correctly from source to target, you have to understand the sentence. This is what humans do. It turns out that you don't have to understand the sentence. And today we know that you don't have to understand absolutely anything, and still you can like pass GCSE exams and win in various competitions and pass legal tests. So this is what is still for you to be done. Okay, so let's go to machine translation, reaching human quality. There are some links. You will get the slides. They're still on my laptop only, but I'll send them to Honza or other organizers, so you can get them later. And I'm teaching this as the summer class at Charles University in Prague. So the slides for my seminar are there, of course, and they are also pre-recorded. So it's now inverted class, so people can watch the lectures. I was even a YouTuber in 2014, I think. So I made short videos, these empty talks, and they are very illustrative, except they are, aside from big data and evaluation, they are today absolutely irrelevant, because this is all pre-neural machine translation. And then there are books by Philip Ken, and also I have one book in Czech, again very old, and there will be more books mentioned at the end of the talk. So, translation is a very narrow task, which is great. I haven't realized before the large language models have ruled the world, I haven't realized how easy the area of machine translation was conceptually. It was not easy to do the translation well, but it was easy to define what you are after. You want to express the same meaning in another language, you want to take some text, previously it was just a sentence, and translate that sentence. Today you expect, or users expect the models to be good at everything, and that totally destroys any way to optimize. Yeah, like it's infinite criteria optimization. I don't know how this should be handled practically. So in machine translation, we were even simplifying the task. We didn't have any writer's ambition. We just preferred literal translation. We didn't attempt to handle cultural differences in any way. It was all actually subsumed by the data. So the joke or illustration that I say here is that the data already contains all the politeness differences between the languages. If it's relevant and for the domain, the data will show that. And that can be illustrated from the example of I think it was like Romanian bilingual children. They were given some soup, and they were English-Romanian bilingual. And the cultural differences are already reflected in the language. When they were talked to in English, these bilingual children, and they got the soup, and they didn't like the soup, it was on purpose a soup they didn't like, they said, no, thank you. And then when they were first being talked in Romanian, and they were given the soup when they were in the Romanian context, they said, no. So the cultural differences were part of the language. So their response was already fit for that thing. And that is also reflected in the training data. So machine translation has been preserving some cultural differences already by the data. Levels of output. Previously we were hoping to get output which is worth reading. Then another level was to get output which is worth editing. And it's important to realize that editing, creating a system which produces translation which is easy to edit is something different than creating a system which creates a translation which is easy to read. So if you are like end user, you are happy with some whatever typos don't really happen, but like grammatical structure divergences, because you can easily recover from that meaning. If you are aiming for the post-editing task, you rather want a translation which is like the most likely to have the fewest edits. So these edits should be local. Doing edits which like change the whole sentence structure will be very expensive for the post editor, but very easy to recover from for the user. So this already changes the objective of that enterprise. But we were aiming to create something which is worth editing, and machine translation today for some languages is, as you will hear, at the human translation quality level, and with large language models it is like that across all the areas. I would still strike out the no editing needed. I would actually urge everybody to read whatever the LLM emits, because yes, you know all the errors that happen there. So level 3 remains risky, and it stays so and will stay so, I think, forever. Okay, so this is a triangle that I have to show. It's by Professor Vokova from Grenoble. Is it 30 years, 40 years? It's very, very ancient. The more you process the source language, the easier it should be for the system to then create the target language. And the interlingua is some goal that would in principle allow you, if you are translating between many languages, not to create n-squared systems for every pair of source and target language, but just linear number of systems. You create just an analyzer and a generator, and then you connect any analyzer with any generator, so you need only n systems to cover n languages. The easier so because the interlingua is not really believed into, because different languages have different like levels of detail, then people always stop somewhat sooner. What we did was parse to something which was close to predicate argument structure of that sentence. We called that deep syntax. The deeper you were in the analysis, the easier the transfer was supposed to be. The sad thing was that the path in this picture is actually longer. So along this longer path in this complex pipeline system, you are likely to collect more errors. So each of these steps is conceptually easier, but if you then feed it with a real input, the errors will accumulate and propagate further down the pipeline. So this path is really longer, and getting this running for practical purposes was very hard. There were sentences which the deep syntactic system processed perfectly, but the average sentences were always non-grammatical already at the input. And this system assumed that they would be grammatical, so it was trying to recover and didn't quite recover. So the only way that the deep syntax and the shallow approach, which I'll mention the phrase-based NP, the only way these systems work in practice was when they were working together. And actually, when the direct translation, the simple approach, had always the final decision. So the clever system was good for, I don't have slides for this, so that's why I'm describing it, and I think it's relevant today as well. So the clever system, which followed the rules and created perfect structure and perfect output, but only for some sentences, was always backed off to, or like governed, and the final choice was done by the shallow statistical system. So that's the way I think it always should be if you want to succeed in practical applications. You should have the rules that apply for most of the cases, but you should not leave the rule-based output. It was not really rule-based, it was statistical-based along the path, but it was rule-based in the sense of like what the type of analysis has to be done there. So the rule-based approaches, the more constrained one, the symbolic ones, have to be overridden by simple statistical back-off techniques. And only this combination is what will give you the best output. Yeah, so, rule-based systems are implemented by linguists. We didn't have many rule-based components, only at the transfer. There were some things, yeah. And until neural empty, it was best to combine the approaches. With neural empty, this was kind of subsumed because, in principle, the deep learning systems are able to learn these intermediate representations, including the interlingua, fully automatically just from the data. There is one thing that I would like you to consider, and it is also relevant for large language models. What is the space of possible outputs? So you are optimizing, you're creating a system which, given some input, will produce some output, and there are some number of options, right? For a single English source sentence, you can consider all sequences of Czech words. That would be many bad sentences, of course. There is a subset of all grammatically correct sentences. So there is already a big restriction of badly formed sentences, so sentences with a clear error compared to sentences which are correct in Czech. But then there is a slightly different set of understandable translations of that source sentence that we are given. And there are just a handful of reference translations that were created by humans. So this is to illustrate that you have a huge space of possible outputs, and then humans produce one or like 5 references and not more. With large language models, when you're asking them to write a story, there are also very many outputs. And then you have the world of the machine translation system, which technically can produce some set of strings. Some of these strings are top scoring candidates for the given input, and then one of them is the single best winning candidate. And if we are lucky, then it's a valid or understandable translation, and if the system would be perfect, then it would actually emit something which we typically had to post-edit into, which is grammatically correct and understandable translation of the source. So this is something that you have to keep in mind, because you are fighting a search space which has many bad outputs, but also possibly many good outputs. So I don't know what is your mother tongue. If your mother tongue is Czech, I'll show you examples. If your mother tongue is different, then make this exercise in your language. How many good translations would this English sentence have? And even though he's a political veteran, the Council Karel Březina responded similarly. So how many good translations can you come up with? And I would like you to just guess some number. And At least 20. And we are talking about string differences. So any change in the string will render a new translation. At least 20, okay? Anybody would say more?
Even if we tried, probably many more.
Yeah, so how many more? Hundreds?
What do you do with the ambiguity here?
Let's assume that that's a perfect question. So this sentence, as such, is taken out of some context. The full context of the real world would disambiguate the sentence. There are many ambiguities within all these sentences. The longer the sentence is, the less ambiguous it is, and some sentences will remain ambiguous even in the full context of the whole world, because you don't understand people at times because of ambiguities as well. Let's assume that we want the full set of translations which for any possible context are okay translation for this sentence. So we union all the ambiguous meanings and then create translation from that. So would you increase the 20?
Yeah, that would be like lower thousands. Maybe.
Lower thousands. So here is some sample list from 71,000 correct translations that were created by 2 annotators. Right? So if we ask a third, these 2 annotators had an overlap of about 200 sentences. So if we ask the third one, we would get to 100,000 correct translations. And if we add a fourth person, we would again get more. So native Czech speakers can read this. All these sentences are okay, right? They render the information structure somewhat differently. They highlight different things. And that is related to the context. In different contexts, you would need different rendering of what is new and what is given. But you are highlighting in different contexts. You are highlighting different things. But that's what I said at the beginning. Like I'm asking, or the union of all this. And if you are not given the context, which was the case of machine translation systems, yes, an ideal machine translation system would emit the full list of possible translations. Now higher dozens of thousands for a single sentence. It's also very important to realize that these sentences differ from each other much more than any of these sentences differs from a badly formed one. If you make an error in any of the sentence, grammatical error, typo, or bad ordering of words, something which is really not licensable and so on, the string difference between this good candidate and bad candidate will be very small compared to the string difference between whatever this one and this one. So you see that the space of possible outputs is extremely scattered, mixed, intertwined good and bad outputs. So there's one Indiana Jones movie where Indiana Jones has to cross a corridor, and the corridor looks like it's tiled, so with tiles. But these are actually tiles. Some of those tiles will break and he would fall down to a deep hole. And some of these tiles are pillars. So that's exactly what the search space looks like. You have to step on the pillar tiles, and next to the pillar tiles there is the tiles that will break and you will fall down. So that's what the reality of machine translation search space looks like, and the very same thing applies, of course, to any generation system. So the large language modeling today is not an exception. Okay, statistical approach. Statistical means information theoretic. We need to specify a probabilistic model. How is the probability mass distributed in this crazy space? So you are now not surprised that the probabilities are extremely low numbers, because they have to cover all the good candidates, and we have listed some, and they also have to cover all the bad candidates. And actually, that's a problem of statistical approaches in general. They are not giving you the borderline. They only rank things based on what is more likely and what is less likely, but they don't tell you this is bad and this is good translation. So that's why not in machine translation, because that was already too complex of a task, but in easy linguistic or computational linguistics task, we were always distinguishing between like tagger and an analyzer, or parser and syntactic analyzer. So this syntactic analyzer was something which was designed to give you the full set of correct outputs. All possible correct outputs, not more, not less, and it was not ranking them. That was the analyzer style. Whereas the tagger or the parser style would just rank some strings, some possible outputs, and it didn't give you this, this borderline. So that's also an important thing, and today we don't have any approach that would like somewhat resemble the analysis. Today we are only after the most probable output, and we don't care if it's good or bad. So actually, even the most probable output can be bad, and today's tools do not at all try to distinguish good and bad outputs, which is also kind of gap in research, I would say. Okay, and then so when you're designing this probabilistic model. Still, like I've just criticized the approach, the statistical approach, but it's the most practical one. These systems are designed to give you the most probable output. So in the most cases, when a user runs the system, the user will be happy. So it's like practically that's the good approach, but conceptually it is wrong because it doesn't distinguish the acceptable and not acceptable solutions. And then for this probabilistic model, you specify how to actually learn the model from the training data. And linguistics used to be helpful when we were designing the models. So how to divide the models, how to divide the inputs into smaller units, and which bits of information are more informative. So like where to look around. These days, and with transform model and self-attention, the model learns by itself where is it important to look at. So and the division into smaller units is hard-coded. It's very close to the actual input. So what do you use in your experiments? Some subwords, right? Or are you aware of that, or not at all? What happens at the very beginning of your whatever processing pipeline? Some tokenization, yes, yeah. And there are people who were, like Orhan Firat from Google, who are even opposed to tokenization, and he would prefer the models to be trained directly on bytes. So not Unicode code points, because there are already too many, right? But bytes. So the model should then learn how to assemble the Unicode, the code point from the sequence of bytes. It's technically possible, or even from bits. So the goal, ideal goal would be to have a model which digests the zeros and ones as they are coming, and then process that. And it is, I think that it's possible. You would just need more training time and a larger model, and it would handle that. And we will be even closer to that. So we don't need linguists to find the units anymore. The model learns like how many things it has to digest, and we do not need linguists to find which bits of information are more informative, because the self-attention learns this also automatically from the data. But you need to show it in the data, and that's now the difficult part. Okay, machine translation has been always based on copying. I would like to advertise for one multimodal parallel corpus. Would anybody know which parallel corpus am I talking about? It's Comenius, Jan Amos Komensky, which is 1542 or something like that. It's the book called Orbis Pictus, and that's like the world in pictures. And it was a textbook for learning Latin, German, and there was also a Czech edition. So it was a trilingual and multimodal parallel corpus, because it was complemented with the image. So here, if you do not read the older script for it's a Latin script, of course, but for German, or if you don't understand Latin, it's like come boy, learn to be clever or educated. So that was the first chapter of that book. So this was used to educate humans. Now we are using the very same data to educate systems. So, statistical machine translation, I hope, have you seen a similar formula in the previous lectures this week? Was there some argmax? Many argmaxes, that's good, okay, yeah. So we are searching for the sentence, for the target sentence, which is most likely according to the probabilistic distribution, which is conditional distribution of target sentences given the source sentences, right? And have you also seen the Bayes decomposition, the noisy channel decomposition? I hope many times, right? So can someone summarize why do we do typically now no longer. But why did we do this decomposition of the conditional probability of the target given source so that it becomes crazily swapped? So someone who didn't know this at the beginning of the week and has heard it this week, can someone summarize? So I always say that the reason why Bayes' law was introduced, why noisy channel was introduced, was that the researchers were looking at this conditional probability and they said, conditional probability, what can we do with that? And the only thing they remembered from the basic statistics class was the Bayes' law. So they just plugged in the Bayes' law and something happened. And so what did happen? The Bayes' law puts in relation the unconditioned probabilities and the conditional ones, and because we are in the maximization, we are not interested in one particular constant. Which constant has been left out in this? So that's an easier question. You're afraid of answering a wrong one. So which probability has been left out in this formula compared to the Bayes' law? Sorry, shout.
P of F?
P of F, yes, the probability of the source sentence. The probability of the source sentence is a fixed number, and it doesn't affect the choice of the target sentence. So we do not need to model it, and that's why the models actually didn't even try calculating that, and that's why they were not emitting probabilities of the sentences, but they were only emitting scores of the sentences, only relative ranking of the candidate sentences. The benefits of using the Bayes' law is that we decompose this single table, and you could think of this as a huge joint table which lists all source sentences and all target sentences. But this huge table would not work in practice because any new sentence would not be listed there. So you need to smooth out the probability somehow. So we are benefiting from this decomposition because instead of one big table, we have two big tables, and one of them is the same one as we had before, just reversed source and target, and the other one is like a probabilistic model or huge table, infinitely huge table of all target language sentences. And by multiplying two numbers, you have a broader range of possible output scores. So, have you discussed smoothing? I guess you have, yes. So one aspect of the smoothing is that there are too few different output values. You have, if you are really running into the biggest problem of smoothing, you have just the probability of 1, and you are assuming that something is certain. Or you have the option that something is impossible, 0 and 1. And that's very few output values. You want to have some fine-grained option of outputs. So if you're looking at the smoothing problem or the lack of smoothing problem, just from this point of view, you get a broader range of numbers if you're multiplying from two tables. Like you get n square, depending on how many options you have in the rows and columns, you have n square options. So that's the smoothing which comes from this. And also technically there was of course the benefit that translation model could have been trained on a different data source than the language model. So the scarce resource back then, parallel text, were necessary only for the language, only for the translation model, and the monolingual texts were very much used by the language model, and the language model could have been stronger, could have been more informative element in the global search for the best output. So this worked best in practice in so-called phrase-based machine translation. Here there was the basic unit of phrase. It's not related to what linguists would call a phrase. It is just a short sequence of words, and the model was simply chopping up sentences into these short strings and recomposing them to create new translations. So this is like a translation dictionary. How is it different from the translation dictionaries that humans are using when they are still using? Has anybody used some translation dictionary in the last 3 years? No, not really. So if you were using a printed translation dictionary, how would it be different from this automatically acquired phrase table.
I mean, it would be an actual book. You'd have to copy things manually.
It would be printed, yes, but how the entries would differ?
I think you just have them like as a table. You just have like phrases and like, you know, their equivalents in a table.
So the thing is that you don't really have phrases in, or
Words.
you have individual words. That's it, yeah.
Like, maybe if it's for a corpus, you have better actual context because you can see where.
So this is without context, and I'm very happy that you are like always considering the context. That's great. Each of these entries is without context. It was just listed as a possible translation. And it was up to the language model to see if it fits or it doesn't fit into that context. But yes, you are observing correctly that there is some kind of internal context in the phrases. So compared to the dictionary, it's not just word-for-word translation, but it is like longer units, and most importantly, the phrase table contained both short and long units. So you have a lot of redundancy here. The same thing was repeated in the phrase table many times. It was there alone, and it was there in various contexts. So the entries were like short and long, and then the search was choosing whether it can use the long phrase or whether it should use shorter phrases. And with using longer phrases, it had the chance to introduce fewer errors, but at the risk of not covering all possible inputs. So the flexibility of the phrase-based approach was in that for domains that were well covered in the training data, it could translate sentences by copying verbatim the full. It was at least 10 words was the limit that was used there. So 10-word sentences were often memorized by the system, and it was perfect in translating them. But when the input was out of the domain, the system very smoothly resorted to using shorter units. I'm sure that this feature of like following longer memorized sequences versus following shorter memorized sequences, but they are all diluted, is also present in the neural language models. It's just it hasn't been kind of analyzed that way when the model is kind of continuing a memorized sequence and when it's switching between these sequences. But I think this is an open avenue for like analysis of what the decoder is actually doing. So the difference between printed dictionary and this dictionary is that there is a lot of redundancy, longer units and shorter units. It's fully inflected forms. That's something that I haven't said so far, and it's worse in some local context. And the fully inflected thing is this example, for example, that they are moving. You would never see this in a printed dictionary. You would only have there to move, or you would have the base form of that word. And in Czech, zareagovat is also like a very specific form of the word, zareagovat. So the fact that the phrase table contained all the conjugated and declinative forms was the technical trick which actually got us rid of all the linguists. So you don't need any language knowledge, the source language knowledge and the target language knowledge, because it is explicitly listed in the data. You do not need to understand the grammar and the morphology. It is there, and that's behind the success of phrase-based MT. The key element in the statistical model was the probability of the individual phrases or phrase pairs between source and target language. Here is again one element of smoothing. So now the probability, according to the translation model, was a product of probabilities of individual phrases. So again, you are smoothing. You are creating more output values for the probability distribution because you are multiplying many things. You need parallel data for this, so we spent quite some time. Here is an evolution from 2006 to 2020 of creating Czech English corpus, and our corpus has grown in size. We started with just under 1 million of sentence pairs and went to 200 million sentence pairs. So this was 2 gigawords, 1 gigaword in English, 1 gigaword in Czech, and Yeah, then what was typically done was some processing of this data. Have you heard of sentence alignment? So sentence alignment is the task when you have two texts, you know that they are translations of each other and you want to find out which sentences correspond to which. You may not be able to read Devanagari, the Hindi script, but all you need to know is to realize that there is some symbol which repeats quite frequently, the danda, and there is a similar corresponding symbol, the full stop. So all you need to know about these scripts is the sentence delimiter symbol. You break the corpus at the sentence delimiters and you immediately see the parallel structure. So there is a Church and Gale dynamic programming algorithm which finds the corresponding sentences even if they do not correspond exactly one-to-one, but they are like close to each other. So the parallel structure is immediately apparent. Then the word alignment, this is something which stopped being useful with neural MT. The sentence alignment was still necessary for neural MT and is no longer necessary for large language models or for because we have like big enough input window so that all fits in there across sentence boundaries. The word alignment, again, I'm not going to describe that, but it's a great example of expectation maximization algorithm for automatic discovery which words are translations of which words, and that again like appears automatically from the data just by co-occurrences and by non-co-occurrences. So if a word is never seen in a sentence pair with some other word, then you know it's not going to be translated like that. The phrase-based MT has eventually failed, and I'll illustrate like why it has failed. This is also a summary of that approach in very short illustration. We have a parallel corpus. It has just two sentence pairs. What we do is we create the word alignments and we create phrases consistent with the word alignment. So these are the automatically extracted basic units. These basic units are then used to translate new sentences. So this is the statistical approach which operates with units, like classical statistical approach. And the sentences say, nemám žádného psa, I have no dog, viděl kočku, he saw a cat. And then we get a new input sentence, nemám kočku, it means I don't have a cat, and you use the puzzle pieces to cover this input. So you say, nemám, I have, kočku, a cat, I don't have a cat. Which is wrong, right? So this is in some the reason why phrase-based MT failed, and actually the model and the design of the model was susceptible to dropping negation. There are two reasons for this. Like, how come that we have lost the negation? Can someone discover that in the app?
Because the negation is built into the verb nemám.
Yes. Exactly. So in Czech, the problem is that in Czech we have double negation. So we inject the negation marker twice in the sentence. In English there is only one negation marker. And the word alignment links this no with the like more apparent negation, which is žádného. But we also have the negation built into the verb. So what is missing here is this alignment link between this no and nemám. If we had that alignment link, then the orange phrase couldn't have been used alone. Simply, it would not be extractable alone because there would be this like crossing link here. But in that case, we would be screwed here because we would not be able to, with this very small training data, we would not be able to translate sentence which doesn't mention the žádného. If we don't have that part, we cannot translate that input. So yes, the negation is here. There is loss. There is the link between no and nemám is lost, and that creates a phrase which is licensing to drop the negation. That's one reason why the loss of negation is more likely, and there is one more reason why why losing negation in phrase-based MT was very likely. And would you know that one? So the first one is the problem in the translation model. The translation model licenses something which is wrong. And the second one is the problem in the language model. The problem in language model is that in your corpus, positive sentences are more likely than negative sentences, plus they are shorter typically than the negative sentences. So the language model has two reasons to prefer the variant which drop negation. So as soon as the model licensed to drop the negation, the language model cemented that and said, we like this sentence better. It's positive, right? So that's why phrase-based empty like stopped. So what went wrong? There were two strong independent assumptions. Phrases cannot be really translated independent of each other. The missing link is something which could have recovered that, but the missing link then would cause coverage issues. We would not be able to translate so many sentences. And the language model is a separate unit. It evaluates the sentence on its own without the source. And that's why it can prefer the positive sentences and forget the very important negation. So these two independent assumptions were causing the fundamental limitation. So let's ditch Bayes' law. So let's model the conditional probability directly. Let's emit the output sentence word by word. So we just decompose this probability of the whole target sentence given the source sentence by first emitting the first word and then emitting the second word condition on what you have emitted and so on. So the whole translation model is changed into a language model, a clever conditional language model. So today with NLP, all translation systems have turned into just conditional language models. And the device that can handle that is deep neural networks. Have you seen a similar slide in the previous days of the week or not? Yes, perfect. So you know word embeddings, and you know how the input sentence is digested and how from that input sentence the decoder autoregressively emits the output sentence, right? Is that clear to everybody? What? Yep.
In this case, are we still talking about words or are we talking about word pieces?
It's not relevant. It's the first systems used words, and they were still not competitive because in the real texts from news that were part of the WMT evaluation, there were too many unknown words. What they did was words which were outside of the small vocabulary, they used some unknown token, and there were papers like how to restore the word which was unknown, how to translate it separately. And then with support units, this problem disappeared, and the support units solved, for one thing, the limited vocabulary size, because there are, if you take a reasonably big parallel corpus, you will easily see 1 million different English word forms. And for the very same text in the parallel corpus, we have 2 million Czech word forms. So you would need one-hot vectors of 1 million or 2 million elements, and that's something which is not trainable. So with support units, which you have hopefully described, this breaks down to some preset number, like 30,000 or 80,000. So the vocabulary problem is reduced, plus the productivity of the vocabulary. So you can cover also unknown words just by decomposing them into smaller units. Of course, it will be like creating sometimes bad words, but sometimes correct words. Yeah. Okay. So what is teacher forcing? Have you talked about teacher forcing? Yeah. So the idea when training this input sequence to output sequence is that you set the weights randomly and you always chop the sentence at one point, and you are training this conditional language model. So the first part of the model digests the input sentence, and the second part is pretended to, or you pretend to the language model, to the decoder, that it has already produced the beginning of the sentence which humans have produced, and you ask for the next word after the current point. So teacher forcing is, so remember, we are not training the model to produce the whole sentence at once. We are always training the model only to produce the next word. When the model will be used, you will feed it with the input sentence and say, continue after the blank, after the beginning of sentence symbol. So give me the first word. and it will give you the first word. And then you will call the model again and ask it, give me the second word, give me the third word, and so on. So this is the inference time. The model is building up the output based on its previous outputs. In training, this would be too expensive. You would have to first like cover the beginning of the sentence, and most importantly, you would not know how a human being would continue after a certain cutoff when the beginning differs from what humans have said. So the teacher forcing is kind of required by the data. You know only how humans have translated the whole sentence as such, and you break the sentence at some point and ask the model to predict the next word, the best possible continuation, and you pretend that it has produced this beginning. So that is the teacher forcing. And the way the model is then evaluated is whether it actually emits the exact expected word at that point. So the models are trained, even today, even transform models, are trained in this teacher forcing way, and that actually gives them credit only when they emit the exact particular token at the exact position as expected. And this is very different from how we understand sentences. So we know that when translating some source sentence, all the elements will have to be said at some point. But it's typically not so important, or there are other factors which influence what should you start with. Only if you say sun, then you have to continue with Francisco. But whether you start with San Francisco or some flowers in your hair is not so important, right? So the choices that the model is making are, in my opinion, too restricted by the particular examples seen in the training data. So the teacher forcing is actually forcing the models to memorize. I'm still surprised that they are able to like generalize beyond this memorization, because this is not the way we're training them. And I attribute this only to the size of the data, which has the flowers in your hair in San Francisco in all possible variations, or like many variations. But still the data is limited. So any synthetic generation of the data is always helpful, because it will kind of reduce the bad effect of teacher forcing. And maybe we could come up with some less teacher forcing approach to the training, so that we would allow for some flexibility in that. But that's simply not done. Okay. So summary so far: statistical machine translation chooses the most probable sentence, and the independence assumptions between the language model and the translation model, the base law, and the phrase independence in the phrase-based translation were harmful. So NeuroMT swapped that with the prediction word by word, just a clever language model. And yeah, we haven't covered subword units, word embeddings, recurrent neural networks for variable length, and the encoder-decoder approach is the only, the architecture is the only thing that we halfway described. In general, the whole field around the year 2014 to 16 has moved from searching for the best minimum translation units to representing words and phrases in continuous space and relating them across the languages. Transform model is something which you have described, so I'm not going to go into details here. There are some great tutorials on that. I would just like to, so transformer takes the input sentence, processes it 6 times, right? And then the decoder thinks 6 times before emitting the prediction for the next word. And there is just one thing that I would like to highlight here. Have you seen some illustration of self-attention earlier this week? Yeah, so you know that it learns when it's thinking 6 times at each of the layers. When it's thinking what this word is related to, it has 8 heads to look around. And for example, for pronouns, one of the heads will definitely focus on the antecedent of the pronoun, because it is highly relevant for the translation task. Another head of the pronoun will definitely look at what the pronoun is, what clause is the pronoun part of. So it is a subject in the subordinate clause. The animal didn't cross the street because it was too tired. So this it was too tired is related to that. And then the other heads are harder to interpret, and actually many of these heads can be pruned, and it would still deliver the same performance. But okay, some training magic. So how do you get the best approach, get the best result from the transform model? You need to use large and clean, high quality training data. So we had that 15 years of data collection and filtration. And when the neural MT came, we simply reused that data, which was a great thing. You have to use subboard units, and we have discussed why that is important. Transformer model size should be in line with your training data size. So previously it was thought that neural MT didn't work for the small data conditions until Rico Senrich actually reduced the model so that it had far fewer parameters, and then the smaller training corpus was sufficient to train these parameters. Typically what helped also was some model ensembling or averaging, so you train multiple models and then had them vote or average their weights. There is some research to be done here with large language models as well. All these LoRa's kind of explored the space of slightly modified weights of some pre-trained model. An extra trick which Martin Poppel from our department discovered was this block back translation. So I mentioned it very quickly. Back translation of monolingual data, very important. What do I mean by that? In translation task, we still had the parallel corpus, which was small in size, and we had this target language monolingual corpus. And neural MT was suffering because it didn't have as much data as the classical statistical MT system had. When Rico Senrich again made use of this monolingual data, then it became, the neural MT got on par with like access to data with the classical statistical, and then it had beaten the classical statistical approach. And the way to use target-side monolingual data in translation is to synthesize the source, so use some earlier version of the system. I don't have slides, I skipped the slides here because we had that already 6 years ago for phrase-based MT. We had the same trick. We actually synthesized source data and that helped morphological rich languages because then we saw examples of word forms in context. So that the approach worked also in phrase-based MT, but it was popularized only by Rico Senrich. And what typically you do is you collect your parallel data, correct your target side monolingual data, back translate the monolingual data to source, and mix these two. And when you mix them, you typically shuffle them randomly. So there are batches which contain some sentence pairs which are authentic and some sentence pairs which are synthetic. Block back translation by Martin Poppel is different. You train, this is training steps, so you're walking along the training corpus, and what happened to Martin Poppel was that he simply forgot to mix in the monolingual data, the synthetic data. So he was training on the authentic data only, and it ran already for some number of days, and he said, oh, I forgot to include the data, the system is not going to work, right? So then he wanted to add this synthetic data, and he did it in a very bad way. He used just the synthetic data. So he totally stopped training. This is like a continuous training. Imagine that the corpus runs across these synthetic and authentic parts. But he was like switching between authentic and synthetic data just accidentally because he forgot to mix them properly together. The baseline, when you mix them properly together, is this thin dotted blue line, and you see that it evolves in the standard saturating way that you see in learning curves. Then when you do the modal averaging, which means that you combine either some good checkpoints or some neighboring checkpoints. Here Martin was combining 8 checkpoints. When you combine the checkpoints, you get better performance. That's the thick blue line. And the interesting thing is the red lines. And that's the system which was trained on this crazy block back translation, the switching between authentic and synthetic data. And you see that there are like camel, what is this called? The camelback, camelback shape, and that's the performance of the model. When the model is trained on the synthetic data, its score on the development set is pretty low, And when it's trained on the authentic data, its score is high. And then when you switch to synthetic data, it very quickly again starts producing outputs which are not so much in line with the reference translations of the development set. And then authentic data again increases that. So you see this crazy divergence or this crazy shape of the learning curve. And when you apply the modal averaging, so you take 8 modals in a window and you do it across all the possible shifts of the window, this averaging actually also finds for you what is the best ratio between the model which was recently trained on synthetic versus the model which was recently trained on authentic data. So if you compare these higher scoring outcomes, they are always the cases when the 8 models are 2 checkpoints from the synthetic training part and 6 checkpoints from the authentic training part. That gives you the best performance, and the performance is much higher than averaging standard checkpoints. So this block back translation is a clever trick, and I relate this to genetic programming essentially. I see it as 2 populations. You have the populations of Czech sentences which are native Czech, and that's the monolingual data which was back translated. So it's perfectly native Czech sentences, no translationese. And then you have the translationese, which is Czech, which was created by human translators, because most of our corpus is originally English translated in Czech, only smaller part is created the other way around. So because of the nature of our parallel data, the parallel data is typically Czech translationese. So now you have 2 populations of expected outputs. One population is the native Czech sentences, fluent Czech sentences, and the other is translationese of English in Czech. And the models trained on these 2 populations have different properties, and mixing them is in some like automatically optimized way is the best thing that you can do, because you need to balance kind of the literalness of the translation with the fluency of the target language. So the block back translation is this clever trick that gave a nice improvement. So how did we reach human translation quality? For that, I need to describe the vicious loop. And here I would like to... Yeah.
Sorry to interrupt. I just have one question related with this. Like, do you have like something to compare with not using synthetic data? Because I need this here. Maybe it's not...
we didn't try it, yeah. So, but it's a very good idea. So you could like try to have whatever formal domain and colloquial domain or speech domain and written text domain. This definitely works for the authentic synthetic, so translationese versus non-translationese. But it
just wondering because maybe like because you mentioned that you are mentioning this in this development set, maybe it's related with the alignment, like if the training data aligns better with the development set. Not the case for synthetic data.
Could be, but in any case, this model was also scored better in human evaluation afterwards. So it gave us an improvement afterwards. So reaching human translation quality, the vicious loop of WMT. Every year, training data sets are prepared. Every year, some baseline systems are potentially prepared. And every year, new source texts are selected. This is very important. Every year, we start from scratch with the new source text. We ask participants in the shared task to provide their MD outputs. We ask humans to provide reference translations, and these reference translations never made it to the internet before the shared task. So this is something which is not done today, and of course it does cost money, but it's important. And this has been done for many years. And then you have the component of manual evaluation. So every year you do the manual evaluation, and every year you have some insights like what worked better, what worked worse. And also, you need to update the manual evaluation as your systems are improving. So this is the research loop of science that can then run infinitely, and you need to gradually improve your evaluation methods because the phenomena are simply being resolved, and the focus of the people has to shift. This is how we evaluated machine translation in 2018. We were showing people the English reference translation. This is something to English translation. And we were showing them the candidate, and the people were indicating on this slider to what extent the black text adequately expresses the meaning of the reference translation. After about 15 judgments, 15 sentences, every annotator stabilizes. So if you collect a large number of judgments, then you can trust these scores. It is interpretable by averaging over many judgments by many people, because different people have different scales, of course. The problem with WMT was that we did cover always quite some number of different non-English languages, and Mechanical Turk didn't have these speakers. And that's the last point. And also for the English part, 30 to 70% of the Turkers were not reliable, and you can discover that easily by injecting errors. And if they score the damaged candidate as high as the non-damaged candidate, then you route the person. You still pay them, so there was like a big loss of money. And these were people who already passed some like quality checks. It was not random people, but still maybe they're not attentive enough to the content. So it was tedious, but well, that's the way what we did. And as I said, this ran over many years, and it is still running even today. So I was lucky to cater for Czech there, and there is I would like to highlight one thing. So you have seen the revolution of large language models in 2022, right? And that's the last line here. So between 2022 and 2023, large language models came back to machine translation. And these days, machine translation systems in WMT are based on large language models. They originally, and we'll talk about that later, originally they come from machine translation because Transformer is from here. But now they came back. And the world is all surprised. We had the very same revolution already in these years, 13 to 16. And that's visible in these scores. For example, the English to Czech translation. I had the highest scoring system in 2013. This was Google Translate. This was our system, which combined the deep syntactic approach and also some grammatical fixing of the outputs. And we were significantly better than Google Translate. In 2015, some Montreal system appeared there. Now, what is that? And in 2016, colleagues of Edinburgh talked to these Montreal people, and they, after some summer school, just put together Nematus, and they won the competition. And we were like losing with our clever approach. So within 1 year, the improvements were reached. Or this system included the subword units, and it included the back translation. So this is what made it work. And in 2017. Nobody was using other than neural approaches. So we have seen this revolution already earlier. So the whole field of machine translation is kind of ready to accept these revolutions. And we have also been fooled by the systems in many ways. And that's what I will be talking later in the caveats. Okay, but anyway, what did happen in 2018 is that I suggested let's avoid reference-based evaluation. In the manual evaluation, we were looking, or the humans, annotators were looking at empty outputs and comparing them to reference translation. So first of all, humans can make errors. That's why it's not so reliable to use reference translations. And second, you cannot compare humans to the machines if you take them as the reference. So we switched to source-based evaluation for some languages. And there, the human evaluator is looking at the empty output and the source text. Of course, the evaluator has to be more educated. It has to be a bilingual person, not just the monolingual person in the target language. But the benefit is that he can compare also the reference translations to the source. So you're putting the humans and machines on the very same scales. It's simply not indicated if it's a human or a machine who created that output, and you get the same scores. And that happened in 2018. Our Charles University Transformer was significantly better than Edinburgh's colleagues. and also better than humans. And we said this is suspicious. So whenever something comes out better than educated humans, something is wrong with your evaluation approach, right? And we knew it already back then. The reason was that in that year, humans were translating whole documents. That's what humans normally do. They translate all the news, the whole news articles. Machine translations were still running on individual segments. And the evaluation was running for individual segments too. And that means there is some similarity between the setup of the machines and the setup of the evaluation. And this similarity gives a benefit to the systems that are more similar. Like the humans are different. The machines operate in a way which is similar to the evaluation. So in this concrete example, the similarity comes from the fact that when you translate the sentence out of context and you evaluate it out of context, you will like the sentence better than if you translate the sentence in context and then you take it out. So the human translations were full of sentences which are taken out of context, and therefore they were not so natural as sentences translated independently out of the context. And this is the similarity between the evaluation that gave the translation system an unfair advantage. We evaluated it then more carefully. This is only for the brave. You see the full source document divided into sentences. We actually didn't ask for evaluating of the whole document, but we asked for a subsequence of 10 consecutive sequences, and the humans were putting here tiny scores for each of the sentences within the context. And they were evaluating the translations according to the full source document and the context of other 10 or in the window of 10 neighboring sentences. So this is of course very time consuming. You need to have educated people for this, but yeah, we did it. And the same system which 2018 was winning against people due to an unfair advantage was really scored as on par with people now with in a fair setting. And the reason for, yeah?
You showed the blue score in one of the previous slides.
This is not blue. This is not black score.
Right, but could you mention why just it's relevant for this case?
Black scores are not relevant.
No, in the earlier slide that.
This one? No, this is also.
No, it was the graph when you were actually doing the training. And
yeah. You're right. So this was black scores. We don't have a human evaluation of all this. Absolutely, that would be extremely expensive. I understand your questions. I think it warrants a nice analysis paper. I don't have any, we really should double check if this hypothesis about the two islands, the population and the mixing of the two islands or something like that, if that is an artifact due to black score evaluation against a fixed reference set. Maybe this could be somewhat estimated if we only post-edited the machine translation outputs and used a mixed depth set which would combine authentic translations and post-edited translations. Maybe that would yeah. So it's worth exploring further. Yeah.
Maybe I missed that. Which is the metric that you're using now?
So this is manual evaluation. This is manual evaluation. It keeps changing. So this year at WMT, yes, there is the slider, but before it's called now ESA, error span annotation. Maybe Ondřej Dušek will talk about error span annotation as well, because his colleagues are trying to do error span annotation with large language models. I'm only starting with that. And this year, you will see the source sentence. You will see the full document. The sentences will be kind of expandable, and for each of the sentences, you will have to mark errors. So in the output, you will highlight. You will not explain why. You will just say, I don't like this, I don't like this. And for some of those errors, you will say, this is a major error. Based on these highlights, it will put the slider somewhere, and then you are still free to move the slider elsewhere. If there is, for example, something which is like context dependent, and you want to indicate that overall this is still not a good translation, even though I cannot pinpoint any error in that sentence, it is bad. So this way we hope to get like a more reliable human translation. But for the numbers here, for For these numbers where we are superhuman, this was the direct assessment, and then for the paper where we convinced ourselves that we are on par with humans, it was the average of overall quality, adequacy, and fluency assigned not by slider but by entering a number between 1 and 10. The reason why humans performed worse than machine or on par with machine on average was that they were simply creating more errors. They were adding more, so this is error bars. So the higher the column, the worse. Humans are orange and system is blue. Humans had 20% more absolute errors in adding context and in dropping context. So they were like shifting context around or shifting content around or dropping it. And they also were shifting the meaning, and they had some other adequacy errors. And they had more errors in grammar somewhat, and of course some more errors in spelling. But at the same time, they were better in resolving ambiguity, and they were better in other fluency errors. So they were not creating fluency errors; they were producing more naturally sounding text than the machine. And on average, this led to significantly better outcome than the machine. So this was the red dot here in the 2018 column, and now it happens more and more across more language pairs that humans are on par with the best system. So the red dots are there where the rank, the bucket of the statistically indistinguishable system at the top level includes human translation, or where human translation is even under that, which doesn't happen often. And you also see in this plot that we are no longer interested in all translation pairs. Translating into English is way too easy, so nobody translates into English anymore, because in text translation it's like English is too well covered by the systems. The vertical bars are the grammatical changes. Neural MT 2 years after the transformer, and 2022 is the large language model baseline. So this, I can skip this. This is just some audit reports, also evaluated now by experts in the domain according to GCSE scoring criteria. So these were auditors from the Supreme Audit of the Czech Republic, and they're looking at translated outputs, and they really indicated that our best system is this light color, is better than the reference in language resources, spelling and morphology, and it's on par in all the other GCSE criteria. Has MT for English to Czech reached its goal? Humans actually understand the source sentence, and if they don't understand, they ask around. So they will call their whatever French friend and check if in French hospitals they are really like shipping patients somewhere or whatever. If the word is strange, they will double check what it means in practice, and they will then explain that, translate it accordingly to what is actually happening. And if they are unable to resolve the ambiguity, they will ideally warn the audience. They will even maybe put a translator's note, like this is unclear what was meant by that. This is very different from what the machine does. The machines are trained on millions of documents. You would have to read for 50 years, 8 hours a day without weekends, to just read our training data. As you know, it's half of that is, or more than half of that is actually synthetic. So do these systems understand in any way? Here is an example of translating a legal text. This is my bad English legalese, supplement number 1 to the English agreement on the sublease apartment. That it is something which I created because I had foreign lessee and I needed some contract for her, and then I translated it back to Czech. This reads as perfect Czech legalese. Dodatek číslo 1 ke smlouvě, let's not read that, let's just focus on some terms. It actually says that the teen end and the teen end, that the teen end on the one hand side and the teen end on the other hand side have agreed. So the teen end and the teen end have agreed to continue with the contract. So this is a perfect Czech superhuman translation, but it labels both parties with the same term, teen end, nájemce a nájemce. So it's totally useless in practice. The reason for this is that in English there is tenant and lessee. Both these terms can be translated as an IMC, but if it's a sublease, then you actually have to refer to one of them with some other Czech word, podnájemce or whatever, not nájemce. And the system doesn't check this, so it creates totally useless translation, that superhuman system. Here is another example, máma mele maso. All Czech speakers would know that this is the first sentence that every Czech child reads in the Czech textbooks. Mom is mincing meat, Google Translate manages that. Let's turn that into a question. Maso mele máma, meat grinds mom, right? So we are stepping out of the training data. Of course, Google is not trained on questions about these very simple sentences. So that's why it's totally screwing up the meaning. Same problem with being translated in Neural MT some years ago, 2019 already. And there, the concept of grinding is lost, is just eating. Yeah?
What is it supposed to translate to?
Say it again, sir?
What is it supposed to translate to?
This is the sentence the sentence is mom is mincing meat.
Yes, I know, but the variation, what should they translate to?
These are just questions. Whether mom is whether mom is mincing the meat, or whether it is mom who is mincing the meat. So the different word or the variations focus on which of the facts are we checking. Whether the meat, whether mom, or the mincing or grinding process. So which are we validating? So in Czech, we express information structure with the word order, and that in English you have to also change like syntactically in the sentence. So maso mele máma, is it mom who is mincing meat? Maso máma mele. How is that in perfect English? What is mom doing with the meat? Is she grinding it? That's the way you would have to say. Yeah.
Okay, but in this case, the English translations get it wrong.
Yeah.
Yeah, I see.
Okay. Our system did it better. Does mom grind meat? I hope that you can confirm that meat mom's grinding, maybe with a comma here, would be grammatically acceptable way of asking for maso máma mele. Actually, maybe here the shift is there is even shift in the focus. So in Czech, I think that maso máma mele is asking about the grinding process or the mincing process, and I think that in English, meat mom's grinding, it topicalizes the meat. So is mom grinding the meat, or is she grinding something else, some vegetables? So here it's grammatically correct, but focusing on different things. So it is actually a bad translation.
Unless you realize it in prosody, you could say meat mom's grinding.
Yeah. Unless you, yeah.
So you could put the focus on
Yeah.
grinding by.
Yeah. But it is at least grammatically correct, and it has not the grinding thing. But if you do one more of the permutations, because Czech allows all the permutations in this question actually, then does mom have meat? We also get it wrong even with this system. And the reason why we are better than the other systems is very likely because of the back translated data. Because we simply saw more questions as well. They were appearing not so much in the parallel text, but in the monolingual text. Okay, transformer caveats. Let's do this, and then let's have a break. I'm running out of time. You don't see it yet. I see that, so I'll see how far we go and what I'll have to skip. So one thing is the unexpected lack of generalization. The transformer models can reach human quality. You just saw that. We were trying to be clever. I think that this was still neural MT, but I'm not 100% sure if this is transformer. But yeah. Anyway, it's neural MT, so it's like encoder-decoder approach. We were trying to be clever about the training. We thought that humans are learning from simple sentences first. Let's also try to mimic this. Let's train the system first on something easy, and then continue with something more complicated. This is the baseline. All sentences in the parallel corpus shuffled. Going from easy to hard sentences, the simple thing what you could do is to sort sentences by length. Shorter sentences are very likely to be simpler. So we sorted them by length. It didn't learn at all. So would you guess why? The reason is that the parallel corpus, 50 million sentence pairs, is deduplicated not at the level of individual sentence pairs, but at the level of like short paragraphs, and that is on purpose. If we deduplicated our corpus at the level of sentence pairs, we would run into the problem that Microsoft Bing had at one of those years. They deduplicated the level of individual sentence pairs, and that meant that for the sentence yes, they had only one translation example in whichever language, and they had also like 20 or 50 examples which translated this yes into yes, thank you. Yes, I'll be there. Yes, whatever. So the Microsoft Bing was then hallucinating this extra content just randomly because it had like two broad options for the single yes. And the yes and yes, the very straightforward translation was represented only once. So the deduplication should not be done too eagerly. It should like be done with some consideration of the frequency of that phenomenon. And the way we did it, deduplicating at the level of paragraphs, is what works reasonably well. We always take a sentence pair and two preceding and two consecutive sentences, and if this window of 5 sentences has been seen before, we don't include that sentence pair. But if the windows are different, we do include that sentence pair. For that reason, we do have duplicated sentences. And when we sort the corpus by length, the model will, when the learning rate is still like steeply going up, when the model is willing to learn, the model is exposed to many repetitions of very boring, simple sentences. And it kind of doesn't learn anything useful. And then at the end, when something interesting finally comes in the corpus, the weights are already too much settled to some bad area. So that's why simply sorting the model, sorting the data by length doesn't work as a good curriculum learning. We did something better. This is when we took windows or buckets of sentences of a particular length. So this is sentences up to 5 words, and we shuffle them within that. So the model learned something, but of course, because it is learning only on short sentences, it will not perform well on the def set, which is sentences of all lengths and all topics, right? When we open the bucket with sentences up to 10 words, the model quickly jumps to this better performance and then again increases its performance gradually. And then we open longer and longer, like buckets with longer and longer sentences. So indeed, at the end, we are slightly higher than the baseline. So the curriculum learning somewhat worked here. The problem is what to do after one epoch. Should you start from scratch, then you will probably go back to this performance. Or should you shuffle the sentences? So it's if you just wait with the baseline approach, you will probably get to the better performance. But then I convinced my student, Tom Kotsmi, to take the same corpus with the buckets in the reverse order. So we started with the longest sentences, mixed with all others actually, and we were closing the buckets, and towards the end we were training only on short sentences. And you see this reverse curriculum path. The beginning seems that the model is learning faster than the baseline, but this is actually a mismeasurement, because this is based on the number of sentences. The sentences are now longer than average because they are like oversampled from the longer part of the corpus. So every sentence brings in more words to train on. This is autoregressive training. You're predicting the next word. So we have actually more instances that we're learning at this beginning here. So this is an unfair advantage. This is mismeasurement. But what is true here is that as we are closing the buckets, the system produces worse and worse outputs. It actually unlearns to produce long sentences. So we were later on looking at what the system is really doing there. And it turned out that transformer is very fragile with respect to sentence length. It is producing sentences as long as the training data were illustrating. And this is much stronger than producing sentences which are in some proportion to the source length. It is not following the source length. It is only following the last training batches in the sentence length. So this is test bin, so sentences of different lengths. Baseline is to use the full training data. That's the baseline is actually the best one here. And then you have models which are trained on sentences of a particular length, of a bucket of like 20 to 30, 30 to 40. And you always get the best performance for that particular length that the model has been trained for. I can skip this. It just says in different words that the transform model mimics the training time sentence length, not the input length. And this is another thing. So you would not be surprised so much that the transformer is unable to produce sentences longer than it has seen. It is somewhat surprising that it cannot produce sentences which are shorter than it has seen, right? But the striking thing is that it cannot produce sentences in the middle of the scene lengths. So we also had a run where we trained on training data which only included sentences 10 to 20 plus 40 to 50 words. And we didn't include any sentence which would be 30 words long. And then when we asked the model to translate a sentence which should be translated into 30 words output, the model simply refuses to emit the end of sentence symbol there. So this is the probability of emitting the end of sentence symbol, and it's non-zero only in the areas where the training examples have kind of licensed that. Yeah? This is the standard positional embeddings. But the trainable ones would be the same thing. Actually, the trainable ones are even worse because it cannot extrapolate. Yeah. So this is the default. This is the sinus. Yeah. So that's an interesting fragility of the model, which we would not realize until we tried. Now another set of caveats. Wishful thinking, and that's your own wishful thinking. So I'll illustrate that for us. We are very fond of syntactic structure. We simply think that if the model somehow handles syntactic structure, it must produce nicer translations, right? Because we have spent decades on developing the tree banks, the theory behind those, the parsers for that, and so on. And it's very easy to inject syntactic information for the source sentence to null empty, to the transformer, because transformer has these beautiful heads, and you can train the head to actually represent the dependency tree of the source sentence. You have 8 heads at hand, so if you steal one of the heads for another part of your objective function, so that the matrix does not represent where to look at the sentence, but what is the governor for this word, then the model can learn to translate and parse the source at the same time. So this is a multitask training, something very fashionable in that year, and we said this must work, it must help translate better. And compared to the baseline, which is 36.66 points, indeed when we demand the model to also parse, and we use the first layer for that, it's not better. If we use the second layer, then we get 1 point something Blay improvement. And then when we demand the parse from the later layers, it is not so good. So it's actually, in the representation, the syntax of the source is easiest accessible from the second layer of the transform model. This is another way to read the result. And it does improve the translation, right? And when you are focusing on translation, it is best to demand that the model understands the source syntax at the second layer. When you're focusing on the parsing, this is unlabeled attachment score, when your main task is not the translation, but the actual parsing, then it's better to demand the model to emit the analysis of the source sentence at the second to last layer. So depending on what is your final goal, and you have 2 components of the objective function. One is your cross entropy on predicting the sentence, and another one is your unlabeled attachment score on the parse of the source. If you are after a translation model, demand syntax from some sooner layer, If you're after parsing and you just use the parallel data as extra, multiple tasks for the multitask training, demand the syntactic parse from something late, right? This all sounds good. We could have written a paper just on this. We did another thing. We demanded also the model to predict this linear tree. This linear tree says that every word depends on the immediately preceding tree. This is no syntax. This is just like sequencing of words, right? So we demanded that one of the heads, any of them, is always predicting this diagonal. And that gives us actually a better improvement in translation than the syntactic analysis. So what we have discovered by this is that when you are forcing transformer to parse along the translation task itself, you are getting an improvement, but you are forcing the transformer to have one of its head be stochastic, not just stochastic, so a matrix which has one in every column and row. You get a better performance as well. So just this regularization of the head is what brings the improvement in translation task, not the syntax. So that's the wishful thinking. We are researchers fond of the syntactic information. We trust that syntactic information is useful for translation. We run an experiment and we see an improvement thanks to the syntactic information. We should have done, and we did, and that's why we published it only in some Mexican journal and not some good conference. We did this stupid baseline test. So this stupid baseline is testing the very same idea and not providing the information that you are fond of and you believe is the source. And if the model still gives you the improvement, then it's not the syntactic information, it is some other factor which plays a role. So stupid baselines. That's the thing that you should remember. So so far we are collecting some take-home messages, and one of the take-home messages is every year new test sets, reference outputs never seen on the internet at all. Update your metrics, manual evaluation methods every year as your methods evolve. And another one, always use stupid baselines. Like assume that the model is trying to cheat you, and it is, right? The models are, and the whole deep learning and machine learning is designed to reach the best performance in the criterion. It is using whatever is available to get that best result. So if you want to validate that your information is useful, do a sanity check with a stupid baseline. Yeah, here is the same thing on the target side. Maria Nadezhde, a colleague from Edinburgh, focused on the syntax on the target side. She didn't do the stupid baseline experiment, so she got an ACL paper. And later we did this stupid baseline experiment. So here, the way it's again that we use multitask training. Have you heard of CCG, combinatory categorical grammars, or not? Combinatory categorical grammars are they are also called super tagging. So the idea is that you assign to every word in the sentence a single tag, super tag, and this tag expresses the syntactic function of that word in the sentence. So when you train a super tagger, it is technically a normal tagger. It assigns a tag to every word. But these tags are rich enough so that you can build the full parse from that super tag, right? So these super tags are like locally stored explicit information about the whole syntactic neighborhood, like where this word fits in the syntactic structure of the sentence. So these super tags can be used to make the model predict the syntactic structure of the target along with the translation. And the way you do it is that you interleave. It has been also shown, I'm not showing that, there were papers where there was the morphological information explicit, like morphological text, interleaved with the words, and it was giving you an improvement because the model was like explicitly thinking about the roles of the morphological roles of morphologically rich languages. In this approach, the model first has to emit what will be the syntactic role of the next word, and then it emits the word. So it says, I will make an object, and then says Obama. And then it says, now I will emit a word with this subcategorization frame, with this valency frame. So it is a word which will require, of course, the subject, and it will also require an object, and it will also require a prepositional phrase. So this is a single element, and this single element describes that the next word is a verb, and the verb syntactically needs the object, needs the subject, and needs some prepositional clause, right? So this is the syntactic structure. Like left of me there is the object, right of me there is first the object, and then later on right of me there is the prepositional clause. So this is the compact notation of that, and then the verb receives. Oh, sorry. And then another noun phrase, which will be the object actually. Yeah. So this gave Maria Nadezhda an improvement. We did another thing. We tried this with transformers and RNNs as well. We tried a multi-decoder, so it's predicting these two sequences independently of each other, or this interleaved output. And we tried the correct CCG text, which is the red line, and we tried also random tags, and we also tried a single dummy tag. So the single dummy tag means that the model is always just making a beep and then word, and beep, a word, beep, word, beep, word. Or you emit some random tag and then the word, and random tag and then the word. And the interesting observation is that, of course, the beeping doesn't work. The beeping doesn't help. The baseline is the blue one, and the red one is the correct CCG tags, and the random tags are very, very close to this syntactic information. Of course, this plot could have been zoomed, and you would see that it is actually better to use the CCG tags than the random tags. But it's so close that it definitely doesn't warrant the use of that complex concept of CCG grammars and the parser and so on. The reason for this is the disbalance between the multiple tasks. So the way I see it for myself is that when the model is expected to predict something very hard, which is the super tag, or something impossible, which is the random tag, then the model kind of gives up. And it knows that at every other position, I have no chance. Okay, I will not try. But because I have no chance at this every other position, at the interesting positions where I can try, I can think longer about my prediction. So effectively, the model, the decoder has double the depth in layers. In the first stage, it uses the layers to prepare what it will emit as translation later, and then it kind of tries or gives up on this CCG super tag or the random tag, and then it continues with preparing what it will emit for the word itself. So this is a non-comparable setting compared to the baseline. So again, you should use the stupid baseline. The stupid baseline is the very same approach, very same input lengths, just a non-informative input. Instead of the clever CCG tags, use random tags. With the beeping, the model focuses on the other thing. It focuses on beeping, and that's very easy, like beep at every other position. So it gives up on the translation. Translation is too difficult. Why should I bother? I get half the score if I just beep right. So that's why the learning simply doesn't work. If your multitask training is in some disbalance, if one of the tasks is too easy compared to the other one, the model will optimize even across the tasks, and it will not focus on the one that you are after. We really should take some break. Let's take it now. Let's skip this. This is some misconception about transfer learning. You would be hoping that when you're training for some language pair which is related to the target language pair, you will get some improvement. It turns out that the relatedness is not so important. It turns out that it's much more important to have your training, the parent training pair bigger, not related. Okay. Let's take a break. And on caveats, and I've warned you that wishful thinking is something which is very common to us. We hope that something works because we have provided some clever idea, and you can very easily be fooled by getting good results for bad reasons. So you should double check with that. And I have another caveat. It's I call it practical importance of emergent properties. So I'm going back to the word level representation. So this is something which is at the very beginning of neural network processing of text, the word embeddings. And you of course know Tomáš Mikolov, graduate from here, and his word2vec, right? You have heard about it many times. So you know about the possibility to kind of calculate where words with some meaning are based on the components of the meaning. And here is the test set. The test set is, I would say, mislabeled because Tomáš talks about semantic properties, which is fine, and then he talks about syntactic properties, and all these syntactic properties in our terms would be actually morphological properties. So deriving the superlative or comparative for an adjective, or deriving various verb forms from the base form. So this is like a morphological text, and we realized that it should be possible to create like a better representation, embedding-based representation of words, which would have some knowledge of the word structure, because Czech words have the prefixes and endings and some stems, and these immediately render some properties, morphological properties of the words. So we created an approach. I'll talk about it later. It's called subgram. It represents the words not as one hot vector, but as a multi-hot vector, and each of these ones in the multi-hot vector corresponds to one substring. So some typical ending will have some element raised in that multi-hot representation. So the multi-hot encoding of the word already contains a fair amount of the morphological structure. And we wanted to compare the performance with word2vec, and unfortunately it didn't work. So we then looked at the test set, and we realized that this word2vec comprehensive test set by Tomáš, which seems pretty big, 8,000 semantic and 10,000 these syntactic or morphological questions, that looks pretty good, but we figured out that it is actually constructed by only 300 distinct word pairs. So the test set is created halfway synthetically by like multiplying all the possible combinations. So under the hood, behind the 10,000 instances, the test set is actually pretty small. So we created a different test set. And so this is like just caveat on evaluation interpretation. Yeah. So we created a different test set, and that different test set was much bigger, based on morphological dictionaries of Czech. So it could cover many more words, and it of course also, because it is harder, led to worse performance of word2vec as it was released. So Tomáš Mikolov's word2vec had 62% like accuracy on finding the corresponding word according to the calculation of like the woman and king and so on. On our test set, the word2vec was not so good. When we tried to replicate word2vec, train it on our data, we didn't get as good performance as Tomáš did, so of course we did something badly. But this is comparable when evaluating it on our data set. It was again much worse. So here the point is, if you see someone's paper or someone's released system, you should re-evaluate it yourself, and maybe the score will be much lower because there are other tricks which are not written in the paper. So you should always try to replicate, and even if you don't replicate, you should at least try to re-evaluate. And the reason why we created this complicated test set was this one. We had this clever approach, this subgram, this multi-hot embedding, like morphologically aware embedding, and it seems to be on par with word2vec, and we knew that this is impossible. We had our clever approach, so it must not be as good as the baseline. So that's why we created this test set. And on this hardware test set, yes, we are twice as good compared to Tomáš Wortůvek. So the first lesson to learn from this is that you should replicate other people's setups, and you will often not get the exact same performance. If your clever approach is not delivering good performance, look at the test set and create an appropriate test set, and by doing that you will typically discover that the original test set is in some way too easy, so then you can show the game. But there is another lesson to learn. If you create just 9 rules, then you will get to performance of 72% or 66% on our test set. So this is the big message for today. Everybody is training huge language models, and they are expecting the language model to do everything, right? This was just for morphology. Spend your time writing 9 rules for your task, and maybe you will get a better performance than the huge complicated device, right? Of course, it is fabulous that the Wortůvek model is able to discover morphology from unannotated data. That is amazing. That is great achievement. But if you are interested in a practical application, try it with rules and you may get much further, right? Lifting it further up from the 72% is difficult, but the unsupervised learning is not there anyway, right? So for practical purposes, try the rules. Yeah? So this is another lesson to take from this. And there is one last lesson, the final evaluation, or the caveat on the ultimate evaluation. The ultimate evaluation is the number of citations, right? So our paper from 2026 was submitted to the conference Text, Speech and Dialogue. Czech one oscillates between Brno and Pilsen on March. It appeared in the closed copyrighted proceedings in September that year, and I think 2 years ago it has 13 citations. The other related paper is the very same idea is implemented by Piotr Bojanowski. That is a 2017 paper. It was submitted to archive when our paper was under review, so the very same idea by a different group of people. And it appeared in DACL in 2017, so much later than we had our paper published. And it has 10,000 citations, right? So that is another message to learn, message to remember. Like, decide where you publish. But I still tend to publish at easy venues because then, the work is done and I can move on. And there is another reason, and I need to highlight that. We didn't release any code at all, and we didn't we didn't implement any fast code. And this is the FastText paper. So the very same idea, complemented with a great tool, is what will give you citation. So, like the open source and the practical usability is what you should do to get to make an impact. Okay, speech translation. I need to look at the time.
Is this test question syntactic questions are open, or
The test set?
yes?
Yeah, the test set is. I think we put it somewhere. It should be. But it's derived from a morphological dictionary. So yeah. Okay, speech translation. You have some sound wave, you have heard a lot about speech recognition, you can transcribe that and you then translate the transcription, or you jump directly to the translation. Note that I'm not synthesizing sound speech, I'm not interested in that, I stick with the text very end. You have probably heard that speech recognition is at the level of human accuracies or word error rates. So this is human level, roughly 6% of words misrecognized, and already in 2017 that level was reached, right? So the speech people are also happy, as we are happy with the superhuman machine translation. So let's put these two superhuman technologies together. You will simply run an ASR system, then an empty system, you will get the performance. Well, turns out that the ASR people recognize lowercase sequences of words, and we need sentences. We cannot plug these things together, right? So we had a project, and we assumed that we will start with these two great technologies and just run them easy project. It was not so easy. we had to segment into sentences, and that's totally different model, and it's still not perfect. And then there is also some uncertainty about the recognition. So if you do not handle the uncertainty in any way, you can easily kind of multiply the errors. We will see an example on that in a moment. And then you also, when you're developing this as a tool, you have to acquire the sound and you have to present the output. I'm not going to talk about the output presentation, but for the end user, you can actually kill the whole usability of the tool if the font is too small or if it appears too quickly. So you have to focus on the presentation issues whenever some users are involved, right? So the deployed pipeline was actually a complex system which was using components across the Europe, and the ASR was done in Karlsruhe, the translation was done in Edinburgh or in Prague. It was real-time routing across Europe and translating speech. So that's one EU project that I was coordinating, and I'm presenting this to show you the complexity of this pipeline, and also to highlight that errors happen everywhere, right? So we had network issues. One of the partners had some overload of the network. The whole system was struggling because the ASR was not delivering things in time. Then we had a slow network. This killed multiple of my demonstrations. That's why I'm not giving a demonstration here today, because I know that's something you will again break. I had multiple problems presenting the system. I tested it on site twice, but I was not given a wired connection. And the Wi-Fi worked perfectly until the audience came. And when the audience came, their laptops have, without people like watching movies, they were just like trying to connect to the network. They didn't have the authorization to connect the network, but they have overloaded the Wi-Fi just by their pings. And that's why I wasn't able to deliver this. Then another error is that people are looking at the outputs over the web interface. If there is the last mile also shared by the participants, this can be overloaded, or their web browsers can be overloaded and the translations don't appear quickly. Very easily, in this complicated setup, you can twice load your network when you are shipping the sound twice. Another problem is that I'll mention another thing. Another thing was just recently. So I have like a blog post about what all can go wrong, and we discovered a new problem just 2 weeks ago. We were giving a demonstration for a remote session. The system was perfectly running, except the remote session was provided by MS Teams. And my colleague was testing it. It worked, except when running MS Teams in Firefox, the sound delivery was chopped and slow. And when we switched to Chrome, it was okay. But he realized this only 10 minutes into the session. So he was delivering a very poor performance because of a local difference setting. So this is like a list of things that can go wrong when you're moving from the lab to the practical setting. Another thing that you have to deal with when translating speech is to acquire sound. So this is actually Ondřej Dušek in one of the presentations, and he was speaking that way, and he had a microphone here, which was causing a trouble to the recognition. We tested whether it is better to use this type of headset with the microphone here or the microphone here. And this one is about 3 points word error rate better, so closer to the mouth is better. If you hold the mic badly, then you also are damaging the performance. If you touch the mic, you're damaging the performance. If you put the mic here, so the end user, the presenter who you are trying to transcribe, can again kill your session. So doing speech translation in real time is a very fragile thing. The reverberations can also kill that. And maybe you have seen similar pictures in the speech recognition talks earlier this week. The volume along the pipeline. So everything can be mismanaged. So you have to follow the pipeline very carefully. So again, this is just a big warning. If you have 2 superhuman technologies and you're just trying to put them together, expect that everything will break everywhere, right? And repeatedly. And you will have to go over like a dozen or dozens, 2 dozens, 3 dozens of different errors. You will be learning on the go, and you will always be fixing one of the errors for good, but then another new error will come. This project ran between 2018 and 2022, and as said, 2 weeks ago we discovered one more new error that we didn't discover before. So yeah, then I have some slides of the realistic ASR quality. We said that it is superhuman, right? 4% error rates. This is what the speaker wanted to say. The speaker wanted to say, you have a bottle. Oh yes, we are situated in the heart of České Budějovice. And in reality, because it was a non-native speaker, he said, you have a bottle. He simply mispronounced the bottle. And then instead of we're situated, he said, we're situated in heart of České Budějovice instead of heart. Well, my pronunciation is also not perfect, probably close to this one. And then was some background noise. A knowledgeable person would be able to understand that as, do you have a bottle? Oh yes, we are situated in heart of Czech, and then he would know that this is some city, but he may not know České Budějovice. Some noise-sensitive ASR, some ASR which is sensitive to the background noise would be able to recognize like, oh yes, the off and nothing more. And if we use some noise-resistant ASR, then possibly it would. This is what we got simply. Like it was because of the noise. We got some better. We are situated. We got some better recognition, but many errors as well. And in ideal, we would really get this full combination. So this is an illustration how the reality differs from the expected performance. This is another slide which says that. For the sake of time, I'll skip that. I'll just say that at the beginning of our project, we were hoping to get a human level of performance, like 4% of error rate. And in reality, on 90-second kind of pitch speeches of high school students, the actual word error rate was 10 times bigger. It was 40 to 50%. And that was by the best system that we had in the project. And Google ASR had a word error rate of 80 to 90%. So that was totally unusable. So the conditions can differ so much that you cannot get any usable performance at all. Then there are also the superhuman machine translation still makes errors. So for example, it mixes up the meanings of words. It is much more difficult if you do not have any clue. It was translated as with the wrong meaning of if. It should have been translated as when, but it was translated as it's very difficult to ask whether you don't have any clue, right? So a small error in translation of a single word can make the sentence very hard to understand. Then there will be errors in like word meanings or domain-dependent things. You can be reported after some profanities. That's when you're presenting on YouTube or whatever. And then these profanities were simply out of vocabulary for the translation system, so it translated those as professional things. And here is what I would like to highlight, and that's the kind of multiplicative error when you have a pipeline of speech recognition and subsequent translation. And the goal of my thesis is twofold. If this twofold is translated as twofold, then it's translated as the goal of my thesis is to fall apart, right? Which is definitely not what I was saying. When you are handling, as a human user, the outputs of the speech recognition systems, and you see the system saying, and the goal of my thesis is twofold, you'll realize that this is probably misrecognized twofold. But if you see that translated into Czech, then it's so distant. The error of folding versus two-fold versus two-fold. The difference in meaning is so different. Is so big that you will not be able to like recover what the original speaker meant, and this is why it's very promising to develop end-to-end speech translation systems which do not explicitly write the bad the transcription in the middle, but still they are kind of on par. It's oscillating. This year still it is still unsure whether it is better to have the pipeline systems or the end-to-end systems. And I would like to highlight the still open goal here towards machine interpreting. So speech translation is at the very high level when you have some input sound and you have some text. Problem is that speech translation is typically done at the level of segments. So artificially, the competitors in shared tasks are given pre-segmented speech. This is very different from reality. In reality, if someone would be interpreting my speech, they would have to click a space bar whenever I finish a sentence to get it to the conditions of the IWSLT shared task. So we were complaining about that in a tackle paper, and we have a tool which converts the whisper model into a model which is capable of processing continuous, like endless stream using windows of speech. So there is quite some big step from processing short speech windows to processing continuous outputs. And one thing which I'm not highlighting here, so I'll just say it, is in our whisper streaming, by doing the repetitive recognitions of the sliding window, we kind of do some self-combination of the system. So we feed the system with multiple variants of the input, always shifted a little bit. And we have these multiple different multiple different outputs to vote. By doing this, it's kind of ensembling the model with itself. By doing this, we are getting a better performance than by just analyzing each window once. So it comes at some computational cost, but when you are moving from window-based processing to a continuous stream, you have these multiple windows and you can get extra advantage from that. So that's what our whisper streaming does. And I said that we are after interpreting, and interpreting is again very different from what interpreters do in machine. Interpreters are rephrasing the original message. And they are rephrasing it for a particular target audience. Of course, interpreters have much harder time than the machines, because the machines can be easily made faster or duplicated. The interpreter only has his brain, and he has to learn some strategies how to handle the time pressure and how to simplify the text so that it can be pronounced in the limited time and so on. So the conditions are different between machines and interpreters, and I think that the best best performance will be delivered by the combination. Again, I don't have these slides here, but we have a system which is able to follow both the original speaker and some simultaneous interpreter, and by this double sourcing, we have the chance to combine these sources and deliver better translations again, or we can at least switch between the sources if, for example, my pronunciation is too bad. And we had a very good experience in the COVID times when unexpectedly people came and were running their speech with a face mask. So the ASR was totally without chances. The interpreter was sitting elsewhere without the face mask and was delivering a processable input. So the best performance will be delivered by a combination of machine and man, and it's interesting area to explore. So far we want to compare humans, and as I was saying for the text translation, we are also trying to do this for the speech area. So we are extending the IWSLT shared task, which is very much similar to WMT. It's just doing the speech processing, and we are adding humans in multiple ways. We are providing a human benchmark, so we feed the same inputs to humans and have them interpret it. And we manually evaluated the systems and the interpreter. And for that we have an evaluation technique, which is very similar to direct assessment. What the annotators are doing is that they are listening to the original speech and they are reading the translations as they appear. Sometimes the translations are by the systems, sometimes the translations are transcribed interpreters in the same time synchronization, and the evaluators are hitting buttons, and they hit 0 when they are like totally lost and don't like the translations, or 1, 2, 3 to indicate the quality of what they have just recently listened to. And with this direct assessment, we just collect the judgments and give the average mark. And in 2022, on TED Talks, our system was scored slightly higher in this direct assessment style, in this continuous rating, than the human interpreter. And on that non-native noisy domain that I was describing with the example about the bottle, the systems were worse. There are lots of caveats here, of course. Because it depends how the interpreter is allowed to prepare for that. If they are given the topic exactly and maybe some like references to the content, not exactly the speech, but what it will be about in more detail, they will be able to perform much better. So this year we are evaluating it again, and this is the results which will appear in RWSLT proceeding soonish. This is the other direction, Czech to English, simultaneous speech translation, and we have some non-native Czech speech, which we didn't evaluate with interpreters because the Czech is very slow. It's people who are trying to learn to speak Czech, so it's too easy for interpreting. And we have Parček, which is Czech parliamentary speeches, and we have 2 interpretings, student interpreting and professional interpreting, and our system ended up in the middle in terms of quality. So we are comparable to the student interpreting and worse in quality than the human interpreting, and we are much faster than the human interpreting. So we see a good chance for future that with this extra time, we can do some more analysis. So the next step, for example, would be to link directly an LLM after that, so that the LLM would be doing kind of sanity checks on the content and hopefully translating better and with some better process. Yep.
Are those seconds?
Or this, I don't know the details. I don't know the details if it's seconds. It could be seconds because 4 seconds is what the interpreters typically have, but I don't know. Yeah, okay. We are also doing some practical experiments with this, and the practical experiments are cross-lingual calls. So you see that there is kind of the gradual sequence. You have a lab exercise where you're translating speech which is delivered to you as individual sentences or segment utterances. And then you have the practical setting when you have some professional speakers speaking in good conditions, and then you have the end user situation where you would like to actually get your message across to a speaker which speaks totally different set of languages, so you don't have any language in common. We call this cross-lingual calls. So we have put together people of different nationalities, and we have tested some calls between them. It was, for example, me and my students. The students are foreign, and on purpose I spoke only Czech. They didn't understand any Czech. They were speaking their mother tongues, which I didn't understand, or I had very vague knowledge. And we were continuing our consultations, for example. So I had some Hebrew student and some Vietnamese student, and one of our consultations was not done in English as always, but it was done in Czech and Vietnamese, and we were relying on the speech recognition and speech translation systems. So here is a summary how badly people understood the other language across the 22 responses. It is a first very small experiment, and we would like to do more. So get in touch if you would like to run some cross-lingual calls about any topic. And 40% didn't understand the other language at all. 17% could understand some basic vocabulary, and another 17% could understand basic vocabulary and the technical terms, because English is very often used. English terms are very often used even in those languages, and yeah, sometimes people could understand somewhat. And rarely we had also fluent speakers, which was typically we also had settings where there were more people than just the two. Yeah. The good thing in this first experiment was that some people said it was already usable by now, and nobody said, I don't think this tool can be fixed at all. So nobody was absolutely, there was nobody who would be totally pessimistic about the tool. So speech translation for a dialogue seems like a thing which can be done. And I don't know, have you tried that? Maybe recent cell phones actually have that. Have you tried running such a call in practice? Not yet. So there is chance, and we like our systems are not bad, and we are kind of on par probably. It really depends whether it is segmented speech. So whether people take explicit turns, which is a very important signal for the translation system to translate, or whether it is continuous speech and people can stop speaking at any time. So this is what we are working on these days. And some people said it was usable but tedious, and some people said here are some tips that you need to fix. It was sometimes this is like the speed of communication. This is something that we need to reevaluate. If you are talking across the language barrier, there will be some penalty. You will be delivering your content slower than what you are after. So this is just subjective assessment, and some people said that they are even at half the pace of what they would like to say. But the majority of people said that they are like 3/4 of their speed because of this slowdown. And this also should be considered similarly as this one in a really comparable setting. So in our case, people were speaking but reading what the other party was saying. And you should also run this for the non-cross-lingual, for the monolingual calls, so that you are speaking and you are only reading what the other party is saying, because that can be also a slowdown, and it also can make the reading can make the call more tedious. So when we were asking for the tiredness of the people, people were 2 or 3 times more tired from these cross-lingual calls than they would have been from monolingual ones, according to this subjective evaluation. Yeah. So the result of this exercise was that it is kind of becoming usable in practice, and at the same time, for low-resource languages, it doesn't really work, and it is interesting in the problems that we observe. So the Czech Welsh test, Welsh was extremely badly recognized. And what I would like to highlight here is that the hallucinations of the system got kind of reverberated in the call. So a colleague of mine in Welsh said something about some like signs, but the signs was mistranslated as newspaper. And then I asked about, we were discussing like how Welsh is supported as a language in the UK. And from that, and he didn't say anything about trains, but somehow trains appeared in the output. And I picked up as a topic, and I started talking about newspapers in trains, and I thought that the Welsh government is supporting Welsh within the UK by providing for free bilingual newspapers in the trains that go from London to that area and to Wales. And this was totally like misrepresented message, and I was double checking, but my double check was not understood correctly, and again we got further, and the topics like diverged very quickly because of translation errors and no way to synchronize on this. And even worse was this mix-up of language and meta-language. So of course the systems had troubles in recognizing the question marks because just the intonation is insufficient for the systems to pick up on that. So very often you need to double check if your party is asking or if they are making a statement. But this is what I call a meta language. So you need to talk about the dialogue itself. And the talk about the dialogue itself is not something which would be well covered in the speech and translation data. So the speech recognizers have troubles putting together sentences when you are like asking. So are you asking or saying this? This is something which the speech recognizers will typically misrecognize, and the translation system will typically mistranslate. So you cannot use natural language to synchronize well with someone who is connected to you only through this muddled channel. This is something which definitely needs to be covered in the training data better. And this is related again to large language models. Like the large language models have outputs for all the possible tasks, but they don't have instructions for those tasks. So this is what is missing in the training data, and that's why instruction training is so difficult, because you need to first create these tasks. So this should be easier for the dialogue management to create synthetic data in this regard, but it is needed. And another recognition or translation errors create content from the meta language. So in Czech, if I say, a vy se ptáte nebo odpovídáte, this ptá, for example, could be recognized as pták, which is bird. So I'm asking if you're asking, but my question, whether you are asking, is translated as something about birds, and then we'll start talking about birds, right? So this meta language, through an error, enters the content of the dialogue, and the dialogue is confused. And when there is just some like a noise or some total like a non-recognizable sound segment for the speech recognizer, very often the speech recognizer will say yes or and you get these false affirmations from the other party. So that's also something which derails the dialogue a lot. So here I'm actually leaving the area of just speech recognition, speech translation into something which would be like communication theory, and natural language processing definitely should deal with the communication theory, and we are starting to like analyze this misunderstanding and how to overcome them. And ideally we would like to, for example, create systems which would follow this dialogue and warn people, oh, there is a high risk of misunderstanding. So this is, by the way, part of the activity that interpreters do. Interpreters not only translate the language, but they also mediate any like cultural differences, and they warn about possible misunderstandings. And this is again something which machines are still totally unable to do. So that's interesting to do. Okay. Another topic: multilingual machine translation. Thinking, what should I select from this? I'll save my time for the last part somewhat. So. Multilingual machine, I'll select something from these slides, and primarily one again caveat message. So multilingual translation is when you have more languages than just the source and target. I've already mentioned transfer learning, so maybe let's very quickly go to the transfer learning part, which is here. Yeah. So, what is the idea behind transfer learning in general, not just in multilingual machine translation? Yeah.
Can you sort of generalize from a smaller group onto, like, if you have, that's general for that, if you have a monolingual source and a bilingual source, but the bilingual source is smaller, you can sort of generalize from the bilingual source onto the monolingual?
Yeah. So That's already specific for some translation in very general terms. So transfer learning is that you have some task which is well documented with data. You have big pile of training data for the task, and the task is vaguely related to the task that you are after, and you have only very small data for the task that you are after. So what do you do and what helps, and this is all the pre-training of large language models. You use whatever data you have to train the model for a start, and then you continue training. That's the cheapest way of doing transfer. You continue training or you fine-tune on the task of your interest, right? So that's what's done normally. And the good thing about the pre-training is that you can also ship this pre-trained model, and it will be usable by many people. So the fine-tuning is typically quick. So we did these experiments in machine translation, and here you can have some big parallel corpus, and then you are after some translation in some different language pairs. The reason for the benefit here, of course, can come from some language similarity, but it also, the pre-training can give you some benefit because remember that the model is capable in principle of emitting any sequence of tokens. And there are many non-native language sequences, like all those ... all the question marks, all the garbled sentences. And if we pre-train the LLM or whatever model we are training, so that it avoids these totally garbled outputs, we are already constraining the search space, and that's useful. So actually any natural language is useful in this regard for pre-training thing. So we did this small experiment, that this is again a warning about misconception or like different expectations. We did this experiment in the language pairs. Imagine you have a Czech English corpus and Estonian English corpus. The Estonian English is much smaller. You are not interested in Czech English translation, you are only interested in Estonian English. But the English part is common, by the way, so you should get some benefit from this. So you would like to benefit from that parent. You have to be clever about the vocabulary. If you would create the subword vocabulary from just concatenating the big and small corpus, the vocabulary would overrepresent Czech, and you are not after Czech. So you need to downscale the Czech and have the Czech and Estonian data comparable when you are creating the balanced vocabulary. The balanced vocabulary will contain Czech, English, and Estonian. And then you train on Czech, Czech English, stop at some point, and continue training on the language pair of interest. So the first example where it works really well is between Czech and Slovak, where they are related languages, very, very closely related. So we have the parent model, which is Czech English, and we have 9 times smaller Slovak English. And when we go from English into first Czech and later Slovak, we get some improvement in blast score. And when we go from Czech and later Slovak into English and then continue later with the Slovak to English training, we get a bigger improvement. This is only natural because the English part is common and it has all the English expertise in the decoder well represented. So that's natural thing. Target side shared, you will get a bigger benefit. Let's look at the Estonian example, where we have different possible parents. We have one English-Estonian corpus, and we always finish, we fine-tune on this English-Estonian. But the question is, what should we pre-train on? So we can pre-train on 3.5 times bigger Finnish English corpus, which is the most related one. We have 16 times bigger Russian English corpus, which is, not related, and it uses a different alphabet. It is Cyrillic and not Latin as Estonian, but it's from the same geographical area. So there could be like similar things talked about. The content could be similar. And we have Czech, which is the biggest. The Czech English corpus has been developed for quite some time. So it's not related, different area, same alphabet, 50 times bigger. Guess where you have the best improvement? So the best improvement doesn't come from the most related language, it comes from the biggest language. So the pre-training, and this is something which probably applies to large language models these days as well. The bigger the parent, the better the performance of any child. So that's the kind of misconception that you want. Yeah.
So the question, you said that you take subsets of the parent set, right?
That's only for the subword vocabulary creation. So for the training itself, you take the whole of that. So this is just to make sure that the subword vocabulary doesn't give you too much, doesn't waste too much of its capacity on the language pair which you are not interested in. Yeah. Thanks for a good question. Yeah. Okay, so this is the first multilingual experiment, and then let's go to the multilinguality section here. Yeah. When you there are multiple setups. You can have more languages than just one on the source, on the target, or on both sides, and you can have them one after another, or so that the system should be capable of processing both, or you can have both of them at the same time. And there are many different situations when this happens, and for example, there are many multilingual organizations where you need to digest any of 50 languages and produce all of them at once. So this calls for like some flexible multilingual setups. The benefits from multi-targets are efficiency. You get translations from like at the same time for all the target languages. And this can be done very easily just by parallelizing. So you train a model, the same model, and use batches and ask the same model to emit the same sentence translated into many different ways. For multi-sourcing, this is great for ambiguity resolution because ambiguous words, for example, the German Schloss can be either a castle or a lock. And when you're translating into English, you don't know if it's a castle or a lock. But if someone has already translated it to French, then you can choose this. You will have this ambiguity result from the French source. And this is also what happens in the multilingual organizations. They have kind of a sequence, but the order of languages varies, in which they create the documents in all the translations. So if they optimize the sequence somehow, or if they use whatever is available at the moment, they can already disambiguate some of these sentences. The nice thing about language models, about the neural models, is that you don't have to create any clever architectures. In early years, there were separate encoders and decoders for the different languages, and only the middle part was trying to convey the information. But what works, and you are not surprised by that, is to just throw the data into one big pot. And you have one training item which has the source in German, and it's labeled with the tag translated into English, and then the expected target is the English sequence, and immediately after that comes another pair which is in English, and it has the tag translate this to Dutch, and the expected output is in Dutch. And you create this multilingual system just by mixing all the tasks together, right? And hopefully it will be benefiting from some of the similarities, but we already know that we maybe are benefiting just from additional volume of natural language sequences. And there is a big risk of catastrophic forgetting. If you are trying to cover too many languages at once, then all the languages will not get into the batch size anymore. You cannot refresh all of them in one batch, so you have some scheduling problems in learning. Those languages which you don't refresh often will be quickly forgotten, as the length issue that I described before the break, right? The nice thing is already in 2016, some interlingua appeared there, a Google paper. So the representations of the decoder as the decoded sentence evolves are close to each other for a particular meaning of the sentence, regardless of the language. So Japanese, Korean, and English live together in a close area of the decoder space, which is nice. Let's skip this and let's mention this another thing. This is Jörg Tiedemann's experiment with 900 Bibles. He trained a system which translated only on the single book, right? So the translations were very bad, but it was trained to translate from any language to English and back. And then he looked at this language tag, into which language should it be translating. And the system, as translation was performing badly, but this language flag actually in the highly dimensional space, then reduced to 2D using t-SNE, was revealing language families. So the model did recognize similarities between languages on just one book. Right? I know it's a thick book, but still it's interesting that this is discoverable there. And I would like to bring up another caveat: the massively multilingual models. So like a Google-sized experiment. Google wants to cover all the languages, so they have data for 105 or so languages, and this is how much data they have for that. This is a logarithmic scale, so they have gigawords for high-resourced ones, and only a couple of dozen thousand. Yeah, I don't know if it's language. It's probably words in parallel corpora. But you see, this is a logarithmic scale, so they have high resource languages and then very low resource languages. And of course, comparing the translation quality across so many languages is difficult, but you can somewhat trust it that the performance is good for the highly covered and bad for the badly covered. So it would be great if they got improvement for the low resource languages, and no loss, thanks to some multilingual models.
Bilingual was English.
Yeah, this is always from English or into English. So the baselines, this is translation quality of bilingual baselines, and I'm not sure if this is into English, but it's not comparable inputs. It's probably hard to compare this with confidence. So what they did is, so this is a natural thing. When you train the standard transformer model, which is the green line here, which is 6 layers, this wide feed-forward networks, and what is 16? 16 is the number of heads, yeah. Because 8 in the encoder and 8 in the decoder probably. So if you train the standard transformer model on the multilingual corpus, where you lump together all the language pairs, then you will see some serious improvement compared to the bilingual baseline for the very low resource languages. It does help. But you will see a degradation for most of the languages, because the transformer is kind of not big enough to remember 100 times more languages. So what they did was to spend a lot of computing resources and run the experiment with increasing the transformer model size. And they were increasing it to 1.3 billion parameters, either by creating the model which is wide, so it has 32 heads and much larger feed-forward dimension, and only twice as many layers, or a deep model which has 16 heads and same dimension as the default, but more layers. And then they also use 3 billion and 6 billion models. So this is like kind of the beginning of the large language models. And it turns out that deep was better than wide for low resource languages. So this is reflected in this plot. And with the biggest one, they were able to get above the baseline of bilingual translation, also for the big languages. So that's an important thing. You create a model and you want it to not only help the small ones, but you want it not to decrease the performance for the big languages. And they even continued further from 6 billion, so this plot corresponds to the one that was on the previous curve, to 50 billion parameters in the later year, and then they claim to have gained 5 Blair points even for the high resource languages. So now the caveat here is, and that's written only in the fine print of that paper in a footnote in the appendix, what is the bilingual baseline? So the bilingual baseline is the standard size transform model. So you are comparing the performance of the standard size transformer model with some model which is 100 times bigger in terms of number of parameters, and you are training this 100 times bigger model with 100 times many languages. Some of these languages are small. So my worry is that these small languages do not quite use their capacity, which is kind of reserved in that 100 times bigger model. And the big languages can then use this extra capacity. So what I asked for, but of course they didn't want to spend the extra resources, would be a fair baseline. A fair baseline, kind of the stupid baseline again here, would be to create the huge model, 50 billion parameters, and train it only with the big language data, the single pair, and not monolingual thing. And I fear that it would actually be better than what they have in the multilingual model. So I think this is again like a way the presentation like makes a success from something which is not guaranteed. It's great that you are getting improvement on these low resource languages. That's perfect, but claiming the gain on the big resource languages is subject to unfair conditions. So this is something that you really need to search under lots of paragraphs hidden in the papers, and very often this is actually not in the papers at all because they are only high-level summaries. So this is in a footnote of an appendix. What is exactly the baseline? Okay, let's totally skip this. Let's just mention an interesting paper. Do llamas work in English? Have you seen that paper or not? Yeah. So that's llamas when they are asked, a particular llama, 7 billion llama version 2. It was prompted to translate from French into Chinese. So it had some few short examples of French, Chinese word pairs, and then there was the French word flare, and it was expected to continue after the symbols in Chinese with the Chinese translation. And this is what happens after these two symbols of the Chinese translation. It first across the 32 layers of this particular llama. What you do, this is called lensing. You attach the softmax earlier. So normally the softmax is applied at the last layer of the decoder, and it makes the prediction about the word. But if you attach the softmax, the same softmax sooner, you kind of look at what distribution of words is being prepared there. And when the llama is thinking what should we continue after the colon, it suddenly thinks about flowers. It moves to the area where the English word flowers is represented, and only later it switches it to the Chinese word for flowers. So this kind of confirms that the llamas are technically in the middle layers thinking in the better represented language. And only at the very end, in the last layers, they switch to the last language. And this is illustrated also here for various model sizes, which doesn't make any difference, and for different tasks. So for the translation task, this is the probability of the fact whether the token belongs to English or to some other language. So in the translation task, it simply thinks about English, it thinks about English tokens, and then only at the end this English token is switched to the corresponding Chinese token. For the repetition task, it's not bringing in the English information, it only thinks in Chinese, and this is some closed test filling, and again it first thinks which word should go into the gap. Yeah.
Said that you're basically attaching the same, like you're projecting the output of some layer using the same measures and then apply something afterwards, right?
Yeah.
So I mean, why can we assume that the very same softmax is going to reveal any information about the previous layers when it's going to be totally different?
Yeah. This is like the risk of the method. It's the best peak that we can get. Yeah, we should not assume that, but there is the residual connection. So it should live in the same vector space in theory. Yeah, so that's the rationale behind that. But of course, yes, it is risky. The paper actually has a nice analysis, and I don't remember the details, and I don't have the time. But it's definitely worth looking at that for an analysis of what is actually happening across the layers. So, from machine translation to LLMs, I'm sure you saw this. Sequence to sequence is extremely flexible. You can train it on any pairs in a supervised way. You can split the transformer into encoder-only things, BERT-like models, and decoder-only things, which is GPT-like model. And these monolingual models can be trained on any text from the internet, which is great. So is pure language modeling good for anything else than language modeling? And ChatGPT has shown to us that, yeah, of course. So for you, is it surprising that if you enter a prompt and finish the prompt with TLDR, that the model will summarize? Do you find it surprising, or you find it surprising? I don't. Right? So I don't find it surprising because TLDR is kind of known delimiter. And in the training data, there is lots of web pages which have this delimiter that the model saw. And it's not so difficult for the model to realize that this delimiter has some text before that and some text after that, and these two texts are short and long, and people are happy when it emits the other variant. So that's, yeah.
Is this an instruction tuned?
No. This is not instruction tuned. This is only trained on all the text from the internet. But all the text from the internet demonstrates that TLDR is the delimiter between the long and short text. I'm not surprised that it summarizes. Similarly, for like answering math questions, there's plenty of math questions with like explained calculations. So the model knows that we'll be happy when it will be juggling with the numbers and entities mentioned in the math problem. And sometimes it is right, and sometimes you are even asking about the very same question that was asked before. And there are many like conversation guides, conversation books, which list phrases in pairs, one language, another language. So it's not surprising that if you then prompt the model with a sequence of one language, another language, one language, another language, it will recognize this written and try to satisfy us with continuing the written and translating. So if the model then delivers translation for one sentence and you ask it to continue, it will very likely emit a related sentence in the source language again and translate it again. So it will like continue the conversation book. And OpenAI get popular with ChatGPT because they trained it in the instruction tuning way. They trained it on question-answer pairs, so the model quickly emits something which seems as answers. You all know problems about this. So can it even translate ChatGPT 4.0? This is last year around this time. It was still not translating this mincing meat as mincing. It was translating as eating. So it doesn't understand any better than other transform models. It is just trained on bigger data. You all are very capable of answering my questions. Are LLM search engines?
No.
No. Are they knowledge bases? No. In some sense, yeah, some textual knowledge, very vague. It depends whether you ask the way the same information was provided in some short text. And if you ask in some bad way, like grammatically wrong English, and someone had a false fact described with this bad English, you are likely to get the false answer because the way you worded your question. Yeah. Do they have a model of the world? Not at all. Do they have a model of themselves? No. Not at all, absolutely not, right? Another related paper. So this is actually a difficult, philosophically thinking, this is difficult to answer because the decoder is autoregressive. So it looks at its own previous output. So it, in principle, can follow up on its own thoughts. And there is some evidence that all our consciousness could be just an illusion of us like seeing our previous thoughts. So like my consciousness is maybe me observing myself a split of a second ago. And in this sense, technically the decoder has this ability, but it has only access to its output because it's teacher forced anyway. It's not trained on its true output. So no, they don't have any model of themselves. When are the answers from NLM reliable?
When they're fact checked.
Say it again?
When they're fact checked.
No.
No.
What is fact check? Like, what is a fact? Like
Fact check. No, when
afterwards?
when you check the facts of it, yes, afterwards. Fact check is.
Yeah.
When you word it in the exact same way as it is in the training data.
Or put differently, when you ask about something which is heavily discussed in internet with agreed answer, and you ask the way this is described in the internet. So when you ask about commonly discussed facts with an agreed upon like output, yes, then they are reliable. And how can we reliably derail them? Well, ask about anything specific, anything new. I even say when I was asking like what are LLMs, I had this slide which where I say or claim that LLMs are professional liars. They are trained in the first phase to be just language models, trained on any text to continue the text. And then this is stolen from the OpenAI paper, Instruct GPT. They train it on question-answer pairs, so this is the instruction tuning. This is a standard supervised tuning, that's perfect. The training to be a liar is the reinforcement learning with human feedback. Because you ask the model to emit multiple possible outputs for a particular task, like explain the moon landing to a 6-year-old. It generates 6 different outputs. You have a reward model that is trained on human preferences of this, and the model is fine-tuned to emit nicer outputs. And this nicer is at the global text level, right? So how can you judge if you have a math proof that mention a bad word, like shit, and is correct, and you have a math proof which is wrong or just misleading or unclear and doesn't mention that bad word? Which of them is better, right? And this is trained on some relatively small set of elements and then multiplied by the like evaluator component there. So this is the relevance, the reinforcement learning with the human feedback. That is something which really strengthens the ability of the model to please us, to produce outputs that we like better regardless the content, and given all the vagueness of the better scale. Yeah. Okay. So the kindergarten lesson, and I'm making an advertisement on the other Ondřej's paper, Leak, Cheat, and Repeat. So have you seen the Leak, Cheat, and Repeat paper? Please do read this. So the kindergarten lesson is test on unseen data, please, right? And that's why we every year for WMT develop new test sets. So when you have training data and you have some test set, you need to extract these sentences. It doesn't make any sense to ask on the known sentences. And you actually would be better by extracting the full text, because then, for example, the Little Red Riding Hood would be extracted and you would be testing if the model is capable of translating the Little Red Riding Hood without seeing it. The problem is that there are many copies, many versions of the Little Red Riding Hood story. So even if you extract one or all instances of that single story, there will be others. So there is some natural repetition in language and some natural repetition in content. And it's difficult to deduplicate. It's unclear how should we deduplicate at this level. So that this becomes problematic with the training data size, but you should try, right? The big problem with models accessible only over API is that you do not know what is in the training data, and you cannot be sure whether the training data has not leaked. So that's the Leak, Cheat, and Repeat paper. There are some attempts, for example, the canary strings. Have you heard of canary strings? So canary string is a crazy sequence that is put at the top of some sensitive like test set. If this particular file with the sensitive test set is digested by an LLM and I ask the LLM to continue the string after 26b6. So if I cover this up and I say continue this, and the model emits the canary string, it has seen the test set. So this is a single single direction implication. I cannot use this test set, the model has seen it. But of course, the test set comes from other sources which do not mention this canary string. So the test data still can be very easily covered by the model, and we would not know. So that's a big problem. The train depth test approach is failing when we cannot access the training data, and it's actually fully failing when we are training on the whole internet. So there is an English saying, and it says, "Great minds think alike," and that's the root of the trouble. So when you are trying to come up with a new question, Google for it. Maybe hundreds of people have already asked the same question and they delivered great answers. So coming up with truly new questions is the problem. We are not able to do that because, well, there are many clever people and all has been already recorded. So I think that generating novel cases is very similar to reaching the speed of light. In theory it's possible, but it's more and more expensive as you go. So it's more and more expensive to invent truly new inputs, right? So testing for generalization is kind of maybe impossible, I don't know. Here is the grade school math paper, GSM symbolic. Have you seen that or not? Yeah, so that's a famous data set of math problems, word math problems, 8,000 of those. And what they did is they replaced the names and numbers and tested the models on these modified. It's exactly the same problems, but just the numbers are different. And if you take gamma, then testing gamma on the original GSM model, the GSM test set will give you 87 accuracy. And if you test it on these varied names and numbers, the different variations, of course, will give you different performance, but the average is around 78 or 79. So obviously, the grade school math problems has leaked to gamma because it knows, or many of the questions have leaked to gamma because it knows that. It's different from llama. Llama performs on average at the same level where it performs for the exact copy of grade school math problems as the variations. So llama was trained better. It has not used this test set, and this is that all the models except the GPT-4o have a degradation on this symbolic variant. Here is another set of plots from that paper, which says that, for example, for gamma, if you do not change the numbers but change only the names in the word problems, you actually get an increase in the performance. So the names are not important, but if you change the numbers, you get a decrease, and if you change both, you are what we already saw. And then what else is interesting here? Yeah, they try to break also the models by adding clauses, maybe deleting clauses and adding clauses to the word problems. And it turned out that removing or adding clauses breaks everybody. For GPT-O mini, removing one clause or adding one clause is okay. That's the P1. It's just a little bit flatter, the distribution. But adding two clauses already breaks O mini as well. So I read this as if OpenAI was training the model and they were clever enough to vary the numbers and names. They used a lot of synthetic data, and they were clever enough to add one unrelated sentence, but they were not clever enough to add two unrelated sentences, right? So I see that as like infinite competition. Who will train on more data? Okay, time's running up. Let me very quickly say what I think of understanding, and then we'll wrap up. So we can see understanding as some kind of alignment of representations. This is the Muse method, Alexis Kono, 2018. You train independent word embeddings on one language pair, another language pair, and then you map the vector spaces numerically. And from that, because some elements are common, like numbers, you can rotate and like reshape the word embedding spaces. By that, you actually extract translation counterparts at the level of words, and this is the basis of unsupervised machine translation. So, so far we have always trained machine translation systems on sentences translated by people, and by this we were actually preventing the systems from learning to understand, because we were giving them what are the expected outputs. The unsupervised machine translation, which is translation trained from non-parallel text, is finally the setting in which we have a chance to force the models to find the meaning, to map, to align the meanings across the languages. So instead of being like disappointed, actually I should now be happy that unsupervised MT is finally opening the door towards achieving understanding through the task of translation. But I must not show the expected answer. So maybe we really should focus more on unsupervised training, because then we will design methods that will make the models understand the basis. If we are, the supervised training is killing the natural way of understanding. Okay. So if machines must discover translation of non-parallel text, they may need to understand. That's the statement that I'm making. And my PhD student has just published a book which is on unsupervised machine translation in the narrow sense, but it has at least a foreword about large language models, because large language models appear, as you saw the llama thinking, they appear to align the representations across languages. So yes, some sort of lexical understanding and understanding of synonyms really appears in the model. So that is one take. Create tasks where some alignment has to be discovered by the models. And another take, which is very similar to what I guess Hinek was talking about in his lecture, is relating human and machine processing of languages. So machines make errors in very unnatural ways, and because language, and that's Hinek's argument, because language is the result of evolution, so the optimization in the communication setting between humans, maybe it is optimized for that communication, and maybe it would be best modeled in the way that it is handled by our brains. So by studying what we actually do and mimicking our thinking and using of languages, we could be able to get models that are understanding more. And by creating models that are more similar to us in their processing of language, we are definitely going to learn more about ourselves, which is interesting. I'm not saying that these models will be better than humans in the particular task, because that's not the point here. The point here is to make it more similar to humans. If you want to make it better than humans, then yes, proceed with the supervised training. Okay, we are at the end. Given all the data we had for statistical SMT, which is thanks to the years of data collection, and then given the big GPUs and some of the training tricks and a few weeks of training time, transformers managed to reach average quality comparable to sloppy humans. That's where we are. No understanding is present in the models. Sometimes they make horrible errors, and they definitely do not generalize in the way that we generalize. With SMT, we made the wrong independence assumptions. With NLP, we can hope to find kind of the blind spots in the representations covered with the data. And with neural networks in general, deep learning systems in general, the intuition why something works is very often wrong. So please, one of the key messages is use trivial baselines to reduce the misinterpretations why something helps. And we grossly underestimate the similarity of the training and test data. We grossly underestimate the repetition of the natural language form and particular content. So when claiming that something has emerged, or when the model generalizes something, be very, very careful. And if possible, train from scratch so that you know what has leaked, but I know that it's impossible to scan the data, And use carefully prepared test sets, diverse and independent. And even that, I think that maybe the singularity, as people call it, comes from our limitations. Maybe we are at the end of our thoughts, and all our thoughts were already like said by others and put on the internet. So the singularity comes from the repetition that we are running in the in circles. Not that singularity is the point where we are running in circles and short of new ideas. Maybe that's a novel or different definition rather than the point where machines reach our performance. Yeah, another book that I wanted to mention, which discusses in particular the transfer learning and also the caveats, the misconceptions about learning, is The Reality of Multilingual Translation. It's available just as PDF from our web. Okay, that's it. Only 20 minutes too much.
Thanks, Ondra. Any questions?
Yeah.
So you said with like direct translation, often there's more success when it's a language that has like a lot of information around it. Like there's like a lot of
where should I? Which part of the talk are you referring to? Say which?
Like with just like one language to another language. You said that there's more success when it's a language that has a lot of like knowledge around it, or a lot of examples.
A lot of data. Yeah, a lot of data. Yeah.
Then with the multi-language ones, there was more like the similarities in language would help.
No. So in the multilingual experiment, that was the transfer learning thing. You had two parallel corpora. So one corpus is Czech and English, which is pretty big, and another was English Estonian. And we measured the size of parallel corpora in number of sentence pairs. So the Czech one was much bigger than the Estonian one, and the experiment here used. So the test set was only focused on the Estonian. So we are only interested in Estonian. So the test set is ultimately fixed. But before we train on the English to Estonian corpus, we first train on some other language pair. And this some other language pair is either related, but only 3 times as big, or it's written in different script and 16 times as big, or it's unrelated, same script, 50 times as big. And this gives us the best improvement.
Okay.
So,
and then what about when it was like English to a bunch of different languages at the same time?
we didn't try that. Yeah, that's... then you would, of course, have to weight which of the languages you like better, which is more important, or equal weights across all the languages. So yeah, that's an interesting setup. So.
What was the example where it was like a German word like Schloss, and then you use the French to like learn that it's possible?
Yeah.
Wasn't that about like using like different languages to help with the eventual English translation?
So the way I was using this French word to disambiguate was on the source. But you are right that if the model is also capable of translating into other languages, it can the representation can realize that there are these two meanings because of the French examples, and then be more aggressive in searching for clues to disambiguate. So being more aware of the meaning difference. So that is definitely a very plausible speculation. I'm not aware of any paper that would evaluate that, so that's calls for your experiment. Yeah. Thanks for a nice idea. So it is. Yes, it is. This is this would be a classical example of multitask training, where there is hope that this additional task help with the original task, and it's multitask on the target side, not on the source side. Yeah. Thank you. Yeah.
For the speech translation, you mentioned the modular approach and some of the issues that came with that. For I guess speech translation, live speech translation is speech to speech. Are there end-to-end approaches as well, and how does that compare to the modular?
So there is this Translatotron paper and others, and I haven't really. If you mentioned speech to speech directly, yeah. So I haven't played with that at all because I don't think that producing. So I think that we are still too far from trying to handle prosody right away. So I think it's better still to produce first the intermediate target text and then synthesize it, than to directly produce the sound. And that's just my personal preference. And for that reason, I do not study the speech-to-speech target. And for that reason, I don't know if like how to we call it onlineize, how to make it working on infinite input. In our approach, we have the windows and we like overlay them, and when multiple windows agree, then we expand the output, right? So that's the confirmation from the multiple overlapping windows is what holds our system back from emitting a word until it is stable enough. And this validation is what increases the quality of after, compared to the baseline, which translates the whole thing in one go, for example. If you did this speech to speech, you would have to have these overlapping the windows of speech signal, and you would be measuring if they are like similar enough. And then you would have to blend them in the same way that panoramas are created from pictures, from photos, to create like a speech-to-speech simultaneous translation system, which is interesting, and it can be definitely a promising direction, but you need different tools for that. So yeah, again, an interesting idea. Thanks. Yep.
These experiments, would that be different if you transfer both encoder-decoder with respect to just the encoder and having decoder for random input?
So now are you talking about the transfer learning? We were too lazy. Our paper is called trivial transfer learning, and it's trivial in the sense that we only switch the underlying data set. And we keep the structure of the network, even and that's quite important, the metadata of the training engine unchanged. If we reset also the training and kept just the weights, then the learning rate would have its spike again very soon, because we follow the norm learning rate, which rises and then gradually decreases. And this spike would erase, it did erase, we did these experiments, it did erase all the gains from the parent. So for us, the trivial transfer learning was the best strategy, and the only thing was that either we had the common language in the source side, in the target side, or nowhere. And even when we didn't have it anywhere, it did help somewhat. And even it did help when the scripts were different in the source pair and target pair. So I attribute this, the gain was of course smaller, but it was there. I attribute this gain to kind of the similarity of natural language strings versus any strings. Yeah, I've talked about this earlier. Yeah, yeah. So I don't have any separate encoder-decoder experiments. Yeah. Thanks. Yeah.
So if there are no more questions, let's thank Ondra again.